This is the story of how astronomers used the James Webb Space Telescope to detect molecules on an alien planet that, on Earth, only come from living organisms, and how the scientific community is now locked in heated debate about whether we've actually found evidence of extraterrestrial life, or stumbled into the most elaborate false alarm in the history of astrobiology. Scientists at Cambridge University announced in April 2025 that they'd identified chemical signatures in the atmosphere of K2-18b with a statistical confidence of 99.7%, and the molecules in question are dimethyl sulfide and dimethyl disulfide, compounds that marine phytoplankton produce in Earth's oceans. The planet sits 124 light-years away in the constellation Leo, and if the Cambridge team is right, we're looking at the strongest evidence yet that life exists beyond our solar system. But that's a massive if, because independent research teams are now publishing contradictory analyses that suggest the signal might be nothing more than instrumental noise. The announcement sent shockwaves through the astronomical community and captured headlines worldwide, with news outlets from the New York Times to the BBC covering the story and sparking intense public interest in what could be humanity's first glimpse of extraterrestrial life. Social media exploded with speculation and excitement, though seasoned astronomers immediately urged caution and pointed out that 3 sigma significance, the technical designation for 99.7% confidence, falls well short of the 5 sigma threshold required for claiming a genuine discovery in physics and astronomy. The gap between these two standards represents the difference between an interesting finding, worthy of follow-up, and a confirmed detection that can be accepted as scientific fact. The Cambridge research team, led by Professor Niku Madhusudan at the Institute of Astronomy, had been studying K2-18b for years, building up a comprehensive picture of the planet's atmospheric composition through multiple observations with different instruments aboard the James Webb Space Telescope. Their work represents the culmination of decades of technological development and scientific effort to build instruments capable of detecting the faint chemical fingerprints of molecules in distant planetary atmospheres. And the fact that we can even attempt such measurements demonstrates how far astronomy has progressed, from just cataloguing dots of light in the sky to actually characterizing the chemical makeup of worlds orbiting other stars. The story of K2-18b begins not with Webb, but with an earlier generation of planet-hunting spacecraft, and understanding how we went from discovering this planet in 2015 to potentially detecting biosignatures in 2025 requires appreciating the rapid pace of progress in exoplanet science. When the first exoplanet orbiting a Sun-like star was confirmed in 1995, astronomers could determine only basic parameters like orbital period and minimum mass, providing almost no information about what these alien worlds were actually like. The discovery of that first planet, 51 Pegasi b, shocked researchers because it defied all theoretical predictions, orbiting its star in just 4 days and challenging everything we thought we knew about how planetary systems form and evolve. Fast forward 3 decades, and we've now discovered more than 5,800 confirmed exoplanets, with thousands more candidates awaiting verification, and our capabilities have expanded from merely detecting the presence of planets to measuring their sizes, masses, densities, and increasingly their atmospheric compositions. This transformation happened through a combination of technological innovation, including space-based telescopes free from Earth's atmospheric interference and clever observational techniques that squeeze every bit of information from the photons reaching our detectors. The transit method that discovered K2-18b, where we measure the tiny dip in starlight as a planet passes in front of its star, has proven spectacularly successful at finding planets, while the radial velocity method that measures how planets tug their stars back and forth through gravitational interactions provides complementary information about planetary masses. K2-18b emerged from NASA's Kepler mission during its extended K2 phase, when 2 of the spacecraft's 4 reaction wheels, which control its pointing direction, had failed, and engineers devised a clever workaround that used solar radiation pressure to stabilize the spacecraft while it continued hunting for planets. The K2 mission shifted its focus to observing different patches of sky for shorter durations compared to Kepler's original mission, which stared at the same 150,000 stars continuously for 4 years. And this new observing strategy allowed the spacecraft to study planets around a more diverse sample of stars, including many red dwarfs like K2-18. The planet showed up as a recurring dimming of its star's light every 33 days, indicating a planet roughly 2.6 times Earth's radius passing in front of K2-18 from our perspective. Initial characterization of K2-18b revealed it belonged to a puzzling class of planets that don't exist in our solar system, and planetary scientists call these worlds mini-Neptunes or sub-Neptunes depending on their exact size, occupying the size range between the largest rocky planets like Earth and the smallest ice giants like Neptune. Our solar system contains nothing in this size range, jumping directly from Earth and Venus at roughly 1 Earth radius to Uranus and Neptune at 4 Earth radii. And this gap led many researchers to initially underestimate how common intermediate-sized planets would be. The reality turned out differently, and mini-Neptunes appear to be the most common type of planet in the galaxy based on the frequency with which they show up in planet surveys. The question of what these intermediate planets are actually made of sparked considerable debate, because you can build a mini-Neptune through several different pathways that produce very different internal structures and surface conditions. One possibility involves a rocky planet like Earth that accumulated a thick hydrogen-helium atmosphere from the protoplanetary disk during formation, creating what's essentially a super-Earth buried beneath an enormous envelope of gas. Another scenario starts with an ice-rich core formed in the cold outer regions of the planetary system that then migrated inward toward its star, where heat from the star evaporates surface ices and inflates the planet's radius. A third option, which has gained attention recently, involves worlds dominated by water throughout their interiors, with high-pressure ice phases deep down, liquid water oceans at intermediate depths, and water vapor in the atmosphere, all blended together into structures quite unlike anything in our solar system. Distinguishing between these scenarios requires measuring not just the planet's size and mass, but also its atmospheric composition, because different formation histories produce different atmospheric chemistries that we can potentially detect through spectroscopy. This is where the James Webb Space Telescope entered the story, bringing capabilities that no previous instrument could match for detailed exoplanet atmosphere characterization, and K2-18b became one of the highest priority targets for Webb's early observations because it combined favourable observational properties, including a bright host star and frequent transits, with the tantalising possibility of being a Hycean world in the habitable zone where liquid water might exist. The detection pushed the boundaries of what the James Webb Space Telescope can measure, and the data sits right at the edge of statistical significance, which means we're either witnessing one of the most profound discoveries in human history, or watching scientists get tripped up by the limitations of current technology. The planet orbits in the habitable zone of a red dwarf star, receiving roughly the same amount of starlight that Earth gets from the Sun, and telescope observations revealed an atmosphere rich in water vapor, methane, and carbon dioxide alongside those controversial sulfur compounds. Everything about K2-18b makes it a prime candidate for a so-called Hycean world, a hypothetical class of planets with global liquid water oceans beneath hydrogen-rich atmospheres, which researchers think could be far more hospitable to life than anyone previously imagined. Nobody's claiming they've found little green men swimming around in alien seas, and the most optimistic scenario involves microbial life comparable to the simplest organisms floating in Earth's oceans, but even that would fundamentally reshape our understanding of our place in the universe. The Cambridge team, led by Professor Niku Madhusudan, spent months analysing spectroscopic data from 3 separate instruments aboard the James Webb Telescope, and they used different wavelengths of infrared light to identify the chemical fingerprints of molecules passing through K2-18b's atmosphere as the planet transited in front of its host star. 2 observations from 2023 provided tantalising hints of dimethyl sulfide, and when they pointed a third instrument at the planet in 2024 and saw the same signal strengthen, they decided the evidence warranted publication. The announcement generated immediate pushback from astronomers who questioned both the methodology and the interpretation, and within weeks, alternative analyses appeared suggesting the mid-infrared data might be corrupted by systematic errors that have nothing to do with actual molecules on the planet. The controversy highlights a fundamental challenge in exoplanet science, which is that we're trying to detect incredibly faint signals from objects trillions of miles away using instruments operating at the absolute limit of their capabilities, and distinguishing real atmospheric features from instrumental artifacts becomes a game of probabilities rather than certainties. statistical confidence levels work differently than most people assume, and a 99.7% confidence means there's a 0.3% chance the signal arose purely by random chance, which sounds impressive until you realise that 3 sigma significance, the technical term for this level, falls well short of the 5 sigma threshold that physicists demand before declaring a discovery confirmed. 5 sigma confidence represents a probability of less than 0.0006% that your result came from statistical fluctuation, and discoveries like the Higgs boson and gravitational waves all cleared this much higher bar before scientists accepted them as real phenomena rather than measurement errors. K2-18b entered the scientific spotlight long before the biosignature controversy erupted, and the planet was originally discovered in 2015 by NASA's Kepler Space Telescope during its extended K2 mission, which used the spacecraft's remaining functional gyroscopes to hunt for planets around red dwarf stars. Initial characterization showed K2-18b to be a super-Earth or mini-Neptune with a mass 8.6 times that of our planet and a radius 2.6 times larger, making it substantially bigger than Earth but considerably smaller than Neptune. The planet completes one orbit every 33 days, circling its star at a distance of roughly 21 million kilometers, which would place it well inside Mercury's orbit if you transplanted it into our solar system. The crucial difference lies in the star itself, because K2-18 is a red dwarf of spectral class M3V, meaning it's cooler and dimmer than our Sun by a substantial margin. Red dwarfs produce most of their energy in the infrared part of the spectrum rather than visible light, and they live for trillions of years compared to the Sun's measly 10 billion year lifespan. But they also tend to be more active, pelting nearby planets with radiation through frequent stellar flares. K2-18 measures about 45% of the Sun's radius, and has a surface temperature around 3,457 Kelvin compared to the Sun's 5,678 Kelvin, which means K2-18b can orbit much closer to its star while still receiving temperate levels of radiation compatible with liquid water. Red dwarf stars dominate the stellar population of our galaxy, making up roughly 70 to 80% of all stars in the Milky Way, and this demographic reality means that most potentially habitable planets in the galaxy probably orbit M-type stars like K2-18 rather than Sun-like G-type stars. The longevity of red dwarfs grants them particular significance for astrobiology, because these stars can support planetary systems for timescales vastly exceeding the current age of the universe, providing ample time for life to arise, evolve, and potentially develop complexity and intelligence if the right conditions persist. The stellar activity challenge facing planets around red dwarfs cannot be dismissed lightly, and young M stars go through a hyperactive phase lasting hundreds of millions to billions of years, during which they produce powerful flares almost constantly. These flares emit intense bursts of ultraviolet and X-ray radiation that could strip away planetary atmospheres through photoevaporation, where high-energy photons hit atmospheric molecules with enough force to knock them into space. The particles in stellar winds, analogous to but more intense than our Sun's solar wind, bombard nearby planets and can erode atmospheres over geological time unless some protective mechanism prevents it. K2-18's moderate activity level, determined through observations of its rotation rate and surface features inferred from brightness variations, suggests the star has passed through its most violent youth and now displays activity comparable to our Sun's, though still elevated compared to older, quieter red dwarfs. Star spots, the stellar equivalent of sunspots where magnetic fields suppress heat, transport from the interior, appear and disappear on K2-18's surface, creating brightness variations that astronomers must account for when analysing transits to avoid confusing stellar variability with planetary atmospheric signals. The question of whether K2-18 hosts additional planets beyond K2-18b and its sibling K2-18c remains open, and radial velocity measurements suggest possible additional companions but haven't yet confirmed them. K2-18c orbits interior to K2-18b with a period around 9 days, and its existence was confirmed shortly after K2-18b's discovery through both transit and radial velocity methods. The two planets might interact gravitationally through orbital resonances, though current observations haven't detected strong dynamical effects that would indicate such resonances are active. Planetary migration theories suggest that K2-18b might not have formed at its current location, but but instead started farther from the star and migrated inward through interactions with the protoplanetary disk of gas and dust that surrounded the young star. Alternatively, the planet could have formed closer to its current position through accretion of solid materials and gas. And distinguishing between these formation scenarios requires detailed modelling of planetary systems and comparison with observed properties. The planet's composition and atmospheric chemistry provide clues about formation history, because planets forming in cold outer regions tend to accumulate more ices and volatile materials than those forming closer in. The tidal forces exerted by K2-18 on K2-18b probably locked the planet into synchronous rotation, where one hemisphere permanently faces the star and the other faces eternal night, though the orbital eccentricity introduces complications that might establish more complex spin-orbit resonances. Tidal locking occurs when gravitational interactions between a planet and its star create friction in the planet's interior that gradually slows its rotation until the same face always points toward the star, similar to how our moon keeps one face toward Earth. The timescale for tidal locking depends on the planet's mass, size, internal structure, and distance from its star, and for a planet like K2-18b, calculations suggest locking should occur within the first few hundred million years. If K2-18b is tidally locked, the temperature contrast between the day and night hemispheres could be extreme unless atmospheric circulation transports heat efficiently from the day side to the night side. Thick hydrogen atmospheres should facilitate this heat transport because hydrogen's light weight allows strong winds to develop that redistribute energy globally, but whether K2-18b's actual atmosphere circulates efficiently remains unknown without direct measurements. A planet with poor heat redistribution might develop a hot day side where water reaches supercritical temperatures while the night side freezes solid, creating a narrow ring around the terminator, the boundary between day and night, where habitable conditions might exist. The concept of terminator habitability has gained attention recently for tidally locked planets, because the twilight zone between scorching day and freezing night could maintain moderate temperatures suitable for liquid water, even if the rest of the planet is uninhabitable. Organisms could potentially thrive in this region, and the perpetual twilight would create unique evolutionary pressures favouring adaptations to low light levels and perhaps leading to chemosynthetic rather than photosynthetic metabolism. Whether K2-18b actually has such zones depends on details we can't yet observe, including atmospheric circulation patterns, cloud formation, and the distribution of any oceans. The planet's orbital eccentricity, measured at around 0.04 according to some studies though with substantial uncertainty, means the orbit deviates slightly from perfect circularity, and K2-18b experiences small variations in the distance to its star over each orbit. Even modest eccentricity can have significant effects through tidal heating, where gravitational flexing of the planet's interior as the star's pull varies, with distance dissipates energy and generates internal heat. Jupiter's moon Io demonstrates extreme tidal heating that powers violent volcanism, and while K2-18b's tidal heating should be far less intense, the process could contribute to maintaining a warm interior and driving geological activity if it occurs. Exomoon possibilities add another layer of speculation to K2-18b's potential habitability, because large moons orbiting the planet could affect its climate through tidal forces that generate additional heating, or by contributing their own gases to a shared atmosphere. Earth's moon stabilizes our planet's obliquity, the tilt of the rotation axis relative to the orbital plane, which helps maintain stable long-term climate, and a similar moon around K2-18b might provide climatic stability beneficial for life. However, calculations suggest that massive moons around planets as large as K2-18b might not survive for geological timescales because the planet's Hill sphere, the region where its gravity dominates over the star's pull, might be too small to retain distant moons, while close moons would spiral inward and eventually crash into the planet due to tidal interactions. The stellar radiation spectrum matters enormously for habitability considerations, because while K2-18 provides roughly the same total energy to the planet as Earth receives from the Sun, the distribution of that energy across different wavelengths differs dramatically. Red dwarfs emit most of their energy in the red and near-infrared rather than visible light, and organisms trying to capture energy through photosynthesis would need different pigments than Earth's chlorophyll, which absorbs primarily blue and red visible light. Whether alien photosynthetic systems can evolve to efficiently harvest infrared light remains an open question, though some Earth bacteria demonstrate limited ability to use near-infrared wavelengths for photosynthesis. The ultraviolet radiation environment differs substantially between K2-18 and the Sun, with red dwarfs producing less UV on average, but experiencing sudden spikes during flares that can temporarily increase UV output by orders of magnitude. Life on K2-18b would need mechanisms to cope with this variable radiation environment, perhaps through developing UV-resistant biochemistry, hiding beneath protecting layers of water or other material, or evolving DNA repair mechanisms even more efficient than those found in Earth organisms. The UV question interconnects with the atmospheric composition question, because different atmospheric gases provide different levels of UV shielding, and a hydrogen-rich atmosphere probably offers less protection than Earth's ozone layer. The host star's age represents a crucial parameter for assessing whether life has had sufficient time to arise and evolve on K2-18b, and estimates place K2-18 at roughly 2.4 billion years old, based on stellar evolution models and observations of rotation rates and surface activity levels. This age means the star and its planetary system are substantially younger than our solar system's 4.6 billion years, suggesting that even if conditions on K2-18b have been continuously habitable since the planet formed, life there has had only about half as long to evolve as Earth's biosphere did. Whether this represents sufficient time for complex ecosystems to develop depends on how rapidly evolution proceeds under K2-18b's specific conditions. Earth's timeline suggests that simple life can arise relatively quickly, within the first few 100 million years, but complexity and diversity require billions of years to develop, and multicellular life didn't appear on our planet until roughly 600 million years ago, just 13% of Earth's history. If similar timescales apply universally, K2-18b might harbour only microbial life, even if organisms colonised the planet shortly after conditions became suitable, and we wouldn't expect to see complex multicellular organisms or intelligence given the system's youth. However, different environmental conditions might speed up or slow down evolutionary rates, making such extrapolation from Earth's example uncertain. The metallicity of K2-18, meaning the abundance of elements heavier than hydrogen and helium, affects what materials were available in the protoplanetary disk for forming planets, and potentially for building biochemistry later. Higher metallicity generally correlates with larger and more numerous planets, and K2-18's metallicity appears roughly similar to the Sun's based on spectroscopic measurements, suggesting the system had adequate raw materials for forming diverse planets and moons. The carbon-to-oxygen ratio in the star, which reflects the ratio in the protoplanetary disk, influences what types of minerals and ices dominate in forming planets, with carbon-rich systems potentially favouring carbide minerals over silicates. The gravitational interactions within the K2-18 system extend beyond just the star and planet, because other unseen planets, planetesimals, or a residual debris disk could influence K2-18b's orbit and climate over long timescales. The migration history of the planets determines their current architecture, and if massive planets migrated through the inner system during the system's youth, they might have scattered smaller bodies and delivered water and organic materials to inner planets through impacts. Understanding the full planetary system architecture requires more observations than currently exist, but the presence of at least 2 planets confirms that K2-18 successfully formed multiple substantial worlds rather than ending up with a single planet or just a debris disk. The system's location in the galaxy, about 124 light-years from Earth in the constellation Leo, places it firmly within our stellar neighbourhood by galactic standards, though the distance still represents an almost unfathomable gulf using current technology. The fastest spacecraft humans have built would take hundreds of thousands of years to reach K2-18 if we launched a probe today, making in situ exploration impossible with foreseeable technology. Even laser sail concepts that could theoretically accelerate tiny probes to significant fractions of light speed would require decades of development and enormous investments to implement, and the travel time would still span many centuries. Communication with any hypothetical intelligent life on K2-18b would face the light speed limit, meaning any message we send takes 124 years to arrive, and we'd wait another 124 years for a response, making dialogue impossible across human lifetimes. This limitation means that even if we confirmed technological civilizations on K2-18b, direct interaction would require patience measured in centuries and societal stability across multiple generations, challenging our ability to sustain long-term projects and maintain interest across such vast timescales. The contrast between our ability to detect and characterize exoplanets and our inability to visit them highlights both the power of modern astronomy and the fundamental constraints imposed by physics. The habitable zone concept gets thrown around frequently in astrobiology discussions, but the boundaries remain fuzzy and depend heavily on assumptions about planetary atmospheres and greenhouse effects. For K2-18, calculations place the habitable zone between roughly 0.1 and 0.2 astronomical units from the star, and K2-18b orbits at approximately 0.14 astronomical units, putting it squarely within this potentially life-friendly region. The amount of starlight hitting K2-18b's upper atmosphere compares reasonably well to Earth's solar constant, meaning the planet isn't too hot or too cold for liquid water to exist on a surface, assuming it has one, and not just an endless ocean extending down to high-pressure ice layers. Early observations with the Hubble Space Telescope in 2019 provided the first tantalizing evidence that K2-18b might have water vapor in its atmosphere, and this represented a major milestone because K2-18b became the first known exoplanet in a star's habitable zone to show confirmed signs of atmospheric water. The finding sparked immediate excitement about the possibility of life, but Hubble's spectroscopic capabilities had limitations that prevented detailed atmospheric characterization, which is where the James Webb Space Telescope entered the picture with instruments specifically designed to dissect exoplanet atmospheres in unprecedented detail. The planet's size places it in an awkward category that doesn't exist in our solar system, and planetary scientists struggle to determine whether objects like K2-18b are scaled-up rocky planets with thick atmospheres or scaled-down ice giants with substantial hydrogen envelopes. Earth has a rocky surface covered partially by water oceans and wrapped in a relatively thin nitrogen-oxygen atmosphere, while Neptune and Uranus are massive worlds dominated by hydrogen and helium, with possible rocky cores buried under thousands of kilometers of high-pressure ices and gases. K2-18b's radius of 2.6 Earth radii puts it in a transitional zone, where multiple internal structures remain plausible. Density measurements help constrain what's inside a planet, and K2-18b has a bulk density around 2.67 grams per cubic centimeter, which falls between Earth's 5.5 grams per cubic centimeter and Neptune's 1.6 grams per cubic centimeter. This intermediate density suggests K2-18b contains a substantial envelope of lighter material surrounding whatever rocky or icy core might exist at the center, but it doesn't uniquely identify whether we're looking at a mini Neptune with a deep hydrogen atmosphere or a water world with a more moderate hydrogen layer. Computer models can reproduce K2-18b's observed mass and radius, using wildly different internal compositions, and distinguishing between these scenarios requires atmospheric observations to reveal what gases surround the planet. The concept of Hycean worlds emerged relatively recently in astrobiology, and the term itself was coined in 2021 by Niku Madhusudan's research group at Cambridge as a portmanteau of hydrogen and ocean. Hycean planets represent a theoretical class of worlds that combine liquid water, oceans with hydrogen-rich atmospheres, and the idea challenges conventional thinking about where life might arise by suggesting that habitable conditions could exist on planets much larger and more massive than Earth. Traditional astrobiology focused almost exclusively on finding Earth-sized rocky planets with nitrogen-oxygen atmospheres, but Hycean worlds vastly expand the potential real estate where life might take hold. The hydrogen atmosphere component might seem counterintuitive for habitability, given that hydrogen doesn't support life as we know it, but the key insight involves recognizing that a hydrogen envelope could create a strong greenhouse effect that keeps surface temperatures moderate even on planets receiving less stellar radiation than Earth. Molecular hydrogen is remarkably effective at trapping infrared radiation, and a relatively thick hydrogen atmosphere could maintain liquid water on the surface of a planet orbiting farther from its star than conventional habitable zones would suggest. This possibility dramatically increases the number of potentially habitable worlds in the galaxy, because the outer edges of planetary systems contain many more planets than the narrow region where Earth-like conditions prevail. Hycean worlds would look nothing like Earth if you could somehow stand on their surfaces, assuming they even have solid surfaces to stand on rather than oceans extending down, until pressure converts water into exotic high-pressure ice phases. The atmosphere would be thick and lightly stratified, with water vapour near the surface transitioning to a hydrogen-dominated region higher up, and the sky might appear hazy or cloudy due to aerosols and condensed water droplets. Surface pressures could be substantially higher than Earth's one atmosphere, potentially 10 to 20 times greater, which would affect everything from the behaviour of water to the types of biochemistry that could function in such an environment. Ocean depths on a Hycean world remain highly speculative, but some models suggest water layers hundreds or even thousands of kilometres deep, far exceeding Earth's maximum ocean depth of about 11 kilometres. The immense pressure at the bottom of such an ocean would compress water into various ice phases that remain solid at temperatures above the normal freezing point, and below these high-pressure ices might lie a rocky or metallic core similar to Earth's interior. Heat from the core could drive convection in the water layer, creating complex circulation patterns that distribute heat and dissolved materials throughout the global ocean, potentially establishing the kind of energy gradients that life exploits on Earth. Temperature gradients drive life on our planet, and Earth's oceans contain thriving ecosystems at hydrothermal vents, where superheated water rich in minerals and dissolved gases erupts from the seafloor. The boundary between hot and cold water creates chemical disequilibrium that organisms harness for energy, and similar processes could theoretically operate on a Hycean world where heat from the interior meets cooler water near the surface. The presence of a hydrogen atmosphere adds another wrinkle, because molecular hydrogen itself can serve as an energy source for certain types of microorganisms, opening up metabolic pathways that don't exist in Earth's oxidizing atmosphere. The habitability of Hycean worlds faces significant challenges beyond the obvious problem that nobody's ever seen one confirmed to exist, and several research groups have published papers arguing that maintaining stable liquid water oceans under hydrogen atmospheres might be harder than initially thought. Hydrogen's greenhouse effect could become too strong, heating the planet until water reaches supercritical temperatures where the distinction between liquid and gas breaks down. Supercritical water exists at temperatures above 374 degrees Celsius and pressures above 218 atmospheres, and while some organisms on Earth survive near these conditions at deep sea vents, the chemical behaviour of supercritical water differs drastically from normal liquid water in ways that might make life impossible. Computer simulations of Hycean atmospheres need to account for how radiation from the host star interacts with hydrogen molecules, and the results depend sensitively on the planet's albedo, which measures how much incoming starlight gets reflected back to space versus absorbed by the atmosphere and surface. High albedos mean more reflection and cooler temperatures, while low albedos lead to more absorption and hotter conditions. Clouds and hazes can dramatically alter a planet's albedo, and whether Hycean atmospheres form reflective cloud decks or remain relatively clear remains an open question that observations need to resolve. The James Webb Space Telescope launched on Christmas Day 2021 aboard an Ariane 5 rocket from French Guiana, and the mission represented the culmination of decades of planning and development that survived numerous budget crises, technical setbacks, and schedule delays that pushed the launch date back repeatedly over 20 years. The telescope arrived at its operational location, the second Lagrange point roughly 1.5 million kilometers from Earth, in January 2022. And it spent several months cooling down to its operating temperature and aligning its 18 hexagonal mirror segments into a single 6.5-meter primary mirror. First light images arrived in July 2022, and the astronomical community immediately recognized they were witnessing a generational leap in observing capability that would revolutionize multiple fields of astronomy, from cosmology to exoplanet science. The engineering challenges overcome during Webb's development bordered on the extraordinary, and the telescope required numerous technological innovations that didn't exist when the project began in the 1990s. The massive primary mirror needed to fold origami style to fit inside the rocket fairing, then deploy and align itself in space with sub-wavelength precision, meaning the mirror segments had to be positioned to within billionths of a meter, despite experiencing the violent shaking of launch and the thermal extremes of space. Each of the 18 hexagonal mirror segments weighs about 20 kilograms and measures 1.3 meters from flat side to flat side, and they're made from beryllium, chosen for its lightweight, strength, and ability to maintain its shape at cryogenic temperatures. The sunshield represents another engineering marvel, consisting of 5 tennis court-sized layers of material thinner than a human hair, each separated from its neighbours by a carefully calculated gap that allows heat to radiate away between layers. The sunshield keeps the telescope and instruments at temperatures below 50 Kelvin, cold enough that the telescope's own infrared emissions don't overwhelm the faint signals from distant astronomical objects, and the temperature difference between the hot side facing the sun and the cold side facing deep space exceeds 300 degrees Celsius. Deploying this enormous structure involved hundreds of precisely timed actuator movements and release mechanisms, any one of which could have failed and doomed the mission, and the successful deployment represented a triumph of engineering and planning. Webb's 4 scientific instruments cover wavelengths from 0.6 to 28 microns in the infrared part of the electromagnetic spectrum, and this wavelength range perfectly matches the thermal radiation emitted by exoplanet atmospheres and the starlight that passes through those atmospheres during planetary transits, while also capturing light from the most distant galaxies in the universe that has been redshifted into the infrared by cosmic expansion. The near-infrared camera, or NIRCam, serves as the telescope's primary imaging instrument and also played a crucial role during mirror alignment, capturing images that engineers used to assess and adjust the positions of individual mirror segments until they all work together as a single optical surface. NIRCam can observe 2 adjacent fields of view simultaneously using separate detector arrays, optimized for short and long wavelengths within the near-infrared range. The near-infrared spectrograph, NIRSpec, represents one of the most sophisticated astronomical instruments ever built, and it can observe up to 200 objects simultaneously using a microshutter array containing roughly 250,000 individually controllable shutters, each comparable in size to a human hair. These shutters can be opened or closed in any pattern to select which objects in the field of view get observed, allowing NIRSpec to take spectra of hundreds of galaxies or stars in a single exposure that would traditionally have required hundreds of separate pointings. The instrument operates in several modes, including multi-object spectroscopy for survey work, fixed slit spectroscopy for studying individual bright objects, and an integral field unit that captures a 3-dimensional data cube with spectroscopic information at every point in a small field of view. The development of the microshutter array alone required over a decade of engineering work to create mechanisms that could reliably open and close hundreds of thousands of tiny shutters repeatedly without failures, and the shutters must operate at cryogenic temperatures in the vacuum of space, while maintaining precise alignment to avoid light leakage that would contaminate the spectra. Each shutter consists of a thin silicon nitride membrane coated with a light-blocking material and held in place by torsion bars that allow it to pivot open when magnetic fields are applied, and the entire array represents a masterpiece of micro-fabrication that pushed the boundaries of what could be manufactured when the project started. The Near-Infrared Imager and Slitless Spectrograph, NIRIS, was contributed by the Canadian Space Agency and excels at detailed spectroscopic observations of individual bright objects, making it ideal for studying transiting exoplanets where you want to capture as much light as possible from a single target. The single object, slitless spectroscopy mode on NIRIS captures the entire spectrum of a target without using a slit to isolate the light, which maximizes signal collection at the cost of requiring more complex data processing to separate the spectral information from contaminating light in the field of view. The instrument covers wavelengths from 0.6 to 5 microns and achieved some of the first exoplanet atmosphere characterizations during Webb's commissioning phase, demonstrating its capabilities by detecting water vapor, carbon dioxide, and other molecules in the atmospheres of several hot Jupiter planets. NIRIS also features an aperture masking interferometry mode that uses a special mask with 7 hexagonal holes placed in front of the detector, and this technique increases the effective resolution of the telescope by creating interference patterns that reveal details about bright objects that would normally be blurred together. The mode works particularly well for observing binary stars that are close together on the sky or for imaging planets very near their host stars, though it only works on relatively bright targets because most of the light gets blocked by the opaque parts of the mask. The commissioning observations demonstrated this capability by clearly separating the components of a close binary star system that would appear as a single blurred blob in conventional imaging. The mid-infrared instrument MIRI operates at longer wavelengths from 4.9 to 28.8 microns and requires active cooling to temperatures below 7 Kelvin to prevent the instrument itself from overwhelming the faint signals it's trying to detect, and a dedicated cryocooler maintains MIRI at its operating temperature, using a helium gas mechanical refrigeration system. The cryocooler represents a remarkable piece of engineering that operates in the vacuum of space without any external cooling source, using compressed helium gas that expands through orifices to achieve temperatures just a few degrees above absolute zero. MIRI's low-resolution spectrograph mode proved crucial for the K2-18b observations, providing an independent check on the molecules detected by NIRIS and NIRSPEC in the near-infrared, while accessing wavelength regions where additional molecular features appear. MIRI can also operate in medium-resolution spectroscopy mode, using an integral field unit that captures spectra across a small region of sky, allowing astronomers to map how gas composition and temperature vary across extended objects like nearby galaxies or protoplanetary disks around young stars. The instrument includes coronagraphs for blocking starlight to observe faint objects nearby, including exoplanets, circumstellar disks, and other structures that would normally be lost in the glare from their host stars. These coronagraphs use specially designed masks that block light from the star while allowing light from surrounding regions to pass through to the detector, and they can achieve contrast ratios, the ratio between the star's brightness and the faintest object detectable nearby, of roughly 10,000 to 1 under ideal conditions. The development and testing of Webb's instruments required specialized facilities where engineers could simulate the temperature and vacuum conditions the instruments would experience in space, and NASA's Goddard Space Flight Center built a massive thermal vacuum chamber specifically for testing Webb's components under cryogenic conditions. The chamber could hold entire instruments while cooling them to operating temperatures and subjecting them to the same level of vacuum they would encounter in space, allowing engineers to verify that every subsystem would function properly once deployed. Testing revealed numerous issues that engineers fixed before launch, and this exhaustive ground testing gave the team confidence that the telescope would work despite the impossibility of hands-on repairs after deployment. Transit spectroscopy works by comparing the spectrum of starlight when a planet passes in front of its star to the spectrum when the star stands alone, and the difference between these two measurements reveals which wavelengths were absorbed by molecules in the planet's atmosphere as the starlight passed through. The technique sounds simple in principle, but requires extraordinary precision in practice because the signals are incredibly small, and when K2-18b transits its star, the planet blocks only about 0.1% of the starlight, a tiny dimming barely detectable even with Webb's sensitivity, while the atmospheric absorption features create variations perhaps a tenth of that, meaning astronomers are hunting for changes at the level of 1 part in 10,000 or less. Systematic errors from the telescope, instrument, or data analysis can easily swamp such subtle signals, which explains why different research teams analysing the same data sometimes reach contradictory conclusions about which molecules are present, and eliminating systematics represents one of the hardest challenges in exoplanet atmosphere studies. Sources of systematic error include anything from thermal variations in the instruments, as the telescope rotates between different pointings, to subtle variations in how starlight falls on different parts of the detector, from charged particles hitting the detectors and creating spurious signals to slow drifts in the telescope's pointing that shift the target's position on the detector over the course of a long observation. Removing these systematics requires careful modelling and statistical analysis, and astronomers develop sophisticated techniques for identifying and correcting instrumental effects, often by observing calibration stars with no known planets to characterise how the instruments behave when no planetary signal should be present. These calibration observations allow researchers to build empirical models of instrumental systematics that they can then subtract from their science data, leaving behind, hopefully, only the astrophysical signal from the planet. The challenge lies in ensuring you don't accidentally remove real signal along with the noise, and different analysis teams make different choices about how aggressively to filter the data, leading to the inconsistent results we sometimes see when multiple groups analyse the same observations. K2-18b's star, being relatively bright at magnitude 13.5, provides enough photons for Webb's sensitive detectors to build up high-quality spectra over multiple transits without requiring prohibitively long exposure times, though magnitude 13.5 still means the star is roughly 2,000 times fainter than the faintest stars visible to the naked eye under dark skies. The planet's 33-day orbital period means transits occur frequently enough that observers can gather multiple data sets within reasonable timeframes, and the 3 transits observed by the Cambridge team spanned from November 2022 to mid-2024, providing time for thorough analysis between observations and allowing the team to refine their observing strategies based on what they learned from earlier data sets. The geometry of the transit determines what part of the planet's atmosphere we actually probe with these observations, and light passing through the atmosphere during transit skims along the day-night terminator region. The boundary between the planet's day and night hemispheres, where the sun sits on the horizon from the planet's perspective. This means transit spectroscopy doesn't tell us about conditions on the day side, where the star beats down continuously, or the night side that never sees direct starlight, and instead we're sampling a twilight zone that might have very different temperatures and chemistry than other parts of the planet. Understanding this geometric bias is crucial for correctly interpreting what the spectra tell us about the planet's overall atmospheric composition and structure. Webb's 4 scientific instruments cover wavelengths from 0.6 to 28 microns in the infrared part of the electromagnetic spectrum, and this wavelength range perfectly matches the thermal radiation emitted by exoplanet atmospheres and the starlight that passes through those atmospheres during planetary transits. The near-infrared camera, or NIRCam, serves as the telescope's primary imaging instrument, and also played a crucial role during mirror alignment, while the near-infrared spectrograph, NIRSpec, can observe up to 200 objects simultaneously using a microshutter array containing 250,000 individually controllable shutters, each comparable in size to a human hair. The near-infrared imager and slitless spectrograph, NIRISS, was contributed by the Canadian Space Agency and excels at detailed spectroscopic observations of individual bright objects, making it ideal for studying transiting exoplanets. The single-object slitless spectroscopy mode on NIRISS captures the entire spectrum of a target without using a slit to isolate the light, which maximizes signal collection but requires careful data processing to extract clean spectra. The instrument covers wavelengths from 0.6 to 5 microns and achieves some of the first exoplanet atmosphere characterizations during Webb's commissioning phase. The mid-infrared instrument, MIRI, operates at longer wavelengths from 4.9 to 28.8 microns and requires active cooling to temperatures below 7 Kelvin to prevent the instrument itself from overwhelming the faint signals it's trying to detect. A dedicated cryocooler maintains MIRI at its operating temperature, and this makes MIRI the coldest instrument on an already frigid spacecraft. MIRI's low-resolution spectrograph mode proved crucial for the K2-18b observations, providing an independent check on the molecules detected by NIRISS and NIRSpec in the near-infrared. Transit spectroscopy works by comparing the spectrum of starlight when a planet passes in front of its star to the spectrum when the star stands alone, and the difference between these 2 measurements reveals which wavelengths were absorbed by molecules in the planet's atmosphere as the starlight passed through. Different molecules absorb light at characteristic wavelengths determined by their quantum mechanical energy level structures, and this creates a unique spectral fingerprint that allows astronomers to identify what chemical compounds exist in an atmosphere they'll never sample directly. The technique demands extraordinary precision because the signals are incredibly small, and when K2-18b transits its star, the planet blocks only about 0.1% of the starlight, while the atmospheric absorption features create variations of perhaps a tenth of that, meaning astronomers are hunting for changes at the level of 1 part in 10,000. Systematic errors from the telescope, instrument, or data analysis can easily swamp such subtle signals, which explains why different research teams analysing the same data sometimes reach contradictory conclusions about which molecules are present. K2-18b's star, being relatively bright at magnitude 13.5, provides enough photons for Webb's sensitive detectors to build up high-quality spectra over multiple transits, and the planet's 33-day orbital period means transits occur frequently enough that observers can gather multiple datasets within reasonable timeframes. The Cambridge team's analysis combined observations from 3 separate transits using different instruments, which should in principle provide robustness through independent confirmation. but critics argue that correlations between the instruments and potential systematic errors affecting all three observations complicate this picture. The molecules that sparked the controversy, dimethyl sulfide and dimethyl disulfide, belong to a family of organosulfur compounds that contain carbon-sulfur bonds. And on Earth, these molecules arise almost exclusively from biological processes, though the 2024 detection on a comet complicated this picture considerably. Dimethyl sulfide has the chemical formula C2H6S, consisting of two methyl groups, each containing one carbon atom bonded to three hydrogen atoms, attached to a central sulfur atom, and the molecule's bent geometry gives it a permanent dipole moment that makes it reactive and volatile. Dimethyl disulfide has the formula C2H6S2, featuring two sulfur atoms bonded together with methyl groups on either end. And this disulfide bridge makes the molecule even more reactive than DMS because sulfur-sulfur bonds are relatively weak and easily broken. Both molecules are volatile, meaning they evaporate readily at moderate temperatures, which explains how they can move from Earth's oceans into the atmosphere where satellites and aircraft can detect them. And both have characteristic odours that humans find unpleasant at concentrations well below 1 part per million. Dimethyl sulfide contributes to the smell of the ocean, along with other sulfur compounds and organic molecules produced by marine life, creating that distinctive briny aroma people associate with beaches and coastal areas, while dimethyl disulfide has an even stronger and more offensive odour, associated with decomposition and spoiled food, though at extremely low concentrations it contributes to the complex flavours of aged cheeses and certain fermented products. The biological production pathway for these sulfur compounds on Earth begins with phytoplankton, and these microscopic organisms occupy the base of the ocean food web, converting sunlight, carbon dioxide, and nutrients into organic matter through photosynthesis while producing roughly half of the oxygen we breathe. Marine phytoplankton, particularly certain types of algae, including dinoflagellates and coccolithophores, produce a precursor compound called dimethyl sulfoniopropionyate, abbreviated DMSP, which serves multiple functions in the cell, including protecting against osmotic stress, temperature extremes, and oxidative damage from excess light and oxygen. DMSP acts as a compatible solute that cells can accumulate in high concentrations without disrupting normal cellular processes, and when phytoplankton cells die or get eaten by zooplankton, DMSP gets released into the surrounding water where bacteria, viruses, and enzymes break it down. The breakdown of DMSP can proceed through several pathways depending on environmental conditions and which microorganisms are present, and one major pathway involves enzymatic cleavage that splits DMSP into dimethyl sulfide and acrylic acid. Certain bacterial species have evolved specialized enzymes that catalyze this reaction, because they can then use the acrylic acid as a carbon and energy source for growth, and the DMS gets released as a byproduct into the water where it eventually evaporates into the atmosphere. The other major pathway involves demethylation, where bacteria remove methyl groups from DMSP sequentially, converting it first to methanethiol and other intermediates before ultimately producing inorganic sulfur compounds, and this pathway doesn't produce DMS, which is why the relative activity of these competing pathways determines how much DMS actually makes it into the air. Marine phytoplankton also produce dimethyl sulfide through direct enzymatic synthesis, using specialized enzymes that Earth's organisms evolved over billions of years, and the discovery of the gene encoding the key DMS-releasing enzyme in 2015 represented a major breakthrough in understanding this process. The enzyme, called ALMA1, catalyzes the breakdown of DMSP into DMS with remarkable efficiency, and its discovery helped explain why some phytoplankton species produce enormous amounts of DMS, while others produce almost none despite containing similar DMSP concentrations. The gene appears in various phytoplankton lineages, suggesting it was either inherited from a common ancestor or transferred horizontally between species through bacterial intermediaries, and its distribution correlates strongly with which parts of the ocean produce the most atmospheric DMS. Dimethyl disulfide forms through oxidation of DMS or through direct synthesis by certain bacteria, and soil bacteria particularly excel at producing DMDS through breakdown of sulfur-containing amino acids like cysteine and methionine. The molecule also forms abiotically when two DMS molecules react with oxygen or other oxidizing agents, though this process typically occurs slowly under atmospheric conditions, and most DMD in Earth's atmosphere probably comes from biological sources even though purely chemical formation pathways exist. The production of DMDS by bacteria degrading organic matter explains why the molecule associates strongly with decomposition and spoilage, as bacteria break down sulfur-containing proteins and other molecules in dead tissue. Dimethyl sulfide plays a surprisingly important role in Earth's climate system, and once it enters the atmosphere, solar radiation breaks it down into sulfuric acid and methane sulfonic acid through a series of photochemical reactions involving hydroxyl radicals and ozone. These sulfur-containing acids condense into tiny aerosol particles that scatter incoming sunlight back to space, creating a cooling effect, and the particles also serve as cloud condensation nuclei, providing surfaces where water vapor can condense to form cloud droplets. This means regions of the ocean with high phytoplankton productivity that produce lots of DMS end up with more low-level clouds, and these clouds reflect additional sunlight, further cooling the surface. The Claw hypothesis, named after the initials of its proposers Charlson, Lovelock, Andrea, and Warren, suggests this represents a climate feedback mechanism where life helps regulate Earth's temperature. According to the hypothesis, if the planet warms up, phytoplankton productivity increases, more DMS gets released, more clouds form, more sunlight gets reflected, and the planet cools back down, creating a negative feedback that stabilizes climate. The hypothesis remains controversial because observations show only weak correlations between DMS emissions and cloud formation in many regions, and other factors like wind speed. Pre-existing aerosol concentrations and atmospheric moisture content probably matter more than DMS for determining cloud properties in most locations. Nevertheless, the basic mechanism of biologically produced DMS influencing climate through aerosol and cloud formation is well established even if the feedback strength is debated. The concentrations of DMS in Earth's atmosphere vary enormously, depending on location and season, ranging from less than 1 part per trillion over continental interiors, far from oceans, to peaks of several hundred parts per trillion over productive ocean regions during phytoplankton blooms. The global average sits somewhere around 50 parts per trillion, and satellite measurements reveal clear geographic patterns, with highest concentrations over the North Atlantic and Southern Ocean, where cold, nutrient-rich waters support abundant phytoplankton growth. Seasonal variations track phytoplankton bloom cycles, with DMS levels spiking in spring when increasing sunlight, and nutrients trigger explosive growth of algae, and declining in winter when productivity drops due to limited light and mixing of the ocean surface layer with deep cold water. Dimethyl disulfide occurs at even lower atmospheric concentrations than DMS on Earth, typically measuring in the low parts per trillion or less, and the molecule has received less scientific attention than DMS despite having potentially important atmospheric chemistry. DMDS absorbs ultraviolet light efficiently, and photodissociates into reactive sulfur radicals that can then participate in complex atmospheric chemistry, affecting the oxidizing capacity of the atmosphere and influencing the lifetimes of other trace gases. The relative neglect of DMDS research compared to DMS research means we know less about its sources, sinks, and atmospheric impacts, which becomes relevant when trying to understand whether detecting these molecules on K2-18b actually indicates biology or could result from unknown abiotic chemistry. The spectroscopic signatures of DMS and DMDS in the infrared wavelength range that Webb observes arise from the molecule's vibrational modes, the ways that atoms in the molecule oscillate relative to each other when the molecule absorbs energy. Carbon-hydrogen bonds stretch and bend at characteristic frequencies that show up as absorption features around 3.4 microns. And these CH stretching modes are particularly strong in DMS and DMDS, because each molecule contains 2 methyl groups contributing 6 hydrogen atoms. The sulfur-carbon bonds also have characteristic vibration frequencies, and various bending modes where groups of atoms move together create additional spectral features at longer wavelengths extending into the mid-infrared region. The problem for identifying molecules from their infrared spectra is that many organic molecules contain similar functional groups that produce similar spectral features, and distinguishing between DMS, DMDS, ethane, and various other small organic molecules based solely on their mid-infrared absorption spectra becomes challenging without very high spectral resolution or observations covering broad wavelength ranges. This ambiguity explains why critics of the K2-18b detection argue that the observed spectral features could be fit equally well by molecules other than DMS and DMDS, and without additional independent evidence, claiming a unique identification may be premature. laboratory measurements of DMS and DMDS absorption, spectra under various temperature and pressure conditions provide the reference data that astronomers use to identify these molecules in exoplanet atmospheres, and considerable effort has gone into measuring precise absorption cross-sections, the measure of how strongly molecules absorb light at each wavelength. These measurements must cover the full range of temperatures and pressures expected in exoplanet atmospheres, from cold stratospheres perhaps 100 Kelvin or less, to hot deeper layers potentially reaching 1000 Kelvin or more, and from low pressures of millibar or less in the upper atmosphere to high pressures of tens or hundreds of bar deeper down. The spectroscopic databases that store these measurements come from decades of laboratory work by multiple research groups, and improving the databases remains an ongoing effort as new molecules of interest emerge and as better experimental techniques become available. Marine phytoplankton, particularly certain types of algae, including dinoflagellates and coccolithophores, produce a precursor compound called dimethyl sulfonylpropionate, or DMSP, which serves multiple functions including osmoregulation and antioxidant protection. When phytoplankton cells die or get eaten by other organisms, DMSP breaks down through enzymatic and bacterial action into dimethyl sulfide, which then evaporates from the ocean surface into Earth's atmosphere. The planet produces something like 20 to 30 million tons of DMS annually through this biological pathway, making it the dominant form of sulfur entering the atmosphere from the oceans. Dimethyl sulfide plays a surprisingly important role in Earth's climate system, because once it enters the atmosphere, solar radiation breaks it down into sulfuric acid and methane sulfonic acid, which form aerosol particles that serve as cloud condensation nuclei. These tiny particles provide surfaces where water vapor can condense, and regions of the ocean with high phytoplankton productivity produce more DMS, which leads to more cloud formation, which reflects more sunlight back to space, which cools the surface and potentially suppresses the very phytoplankton blooms that started the process. This feedback loop, sometimes called the claw hypothesis after the initials of its proposers, represents one of the ways life on Earth might actively participate in regulating the planet's climate. Dimethyl disulfide has a similar biological origin on Earth, produced when bacteria break down sulfur-containing organic matter, and like DMS it evaporates readily and contributes to atmospheric sulfur chemistry. The spectral signatures of DMS and DMDS overlap significantly in the infrared wavelengths that Webb observes, meaning the instruments can't easily distinguish between the two molecules based solely on their absorption features. The Cambridge team's analysis suggests one or possibly both molecules are present in K28B's atmosphere, and they estimate concentrations exceeding 10 parts per million by volume, which is thousands of times higher than the parts per billion levels found in Earth's atmosphere. This concentration difference immediately raises questions about whether biological processes could actually produce DMS or DMDS in such quantities, and it hints that either K218b harbours vastly more productive oceans than Earth, or some non-biological chemistry unknown on our planet manufactures these molecules through abiotic pathways. The Cambridge researchers argue that no known abiotic process can explain the observed abundances, but critics counter that our understanding of chemistry under exotic planetary conditions remains incomplete. And we shouldn't assume that what's impossible on Earth stays impossible everywhere. The story of how these molecules were detected begins in 2022, shortly after Webb became operational, when Madhusudan's team successfully competed for telescope time through NASA's General Observer Program. The awarded program, designated GO 2722, allocated time for 3 transit observations using Webb's 3 main spectroscopic instruments to build a comprehensive picture of K218b's atmospheric composition. The first observation occurred in November 2022 using NIRISS in its single-object slitless spectroscopy mode, capturing starlight from 0.8 to 5 microns as the planet crossed in front of its star. Processing the raw data took months of careful work to remove instrumental artifacts, correct for systematic effects, and extract the planetary transmission spectrum from the stellar spectrum, and the team published their initial results in September 2023 in the Astrophysical Journal Letters. The 2023 paper reported confident detections of methane and carbon dioxide in K218b's atmosphere at levels consistent with a hydrogen-rich envelope over a water-dominated interior, and importantly they noted the near absence of ammonia, which would be expected in a reducing atmosphere but gets depleted if liquid water is present because ammonia dissolves readily. Buried in the 2023 analysis was a tantalizing hint of something unexpected, and at a single wavelength near 3.4 microns, the spectrum showed a small dip that could potentially match the absorption signature of dimethyl sulfide. The signal barely rose above noise levels and the team treated it with appropriate skepticism, but they flagged it as something worth investigating with additional observations. The detection significance was too low to claim a discovery, perhaps 1 or 1.5 sigma at best, which translates to something like a 15 to 30% chance the feature arose from random statistical fluctuations rather than representing a real molecule. The second observation came in early 2023 using NERSpec's high-resolution grating mode, covering wavelengths from 3 to 5 microns with greater spectral resolution than NIRIS could provide, and while the data quality proved excellent and confirmed the methane and carbon dioxide detections, the wavelength coverage didn't include the regions where DMS and DMDS have their strongest absorption features. The team knew that definitively testing for these biosignature molecules required mid-infrared observations that could access the 6 to 12 micron range, where sulfur-containing organic molecules show distinctive spectral fingerprints. MIRI's low-resolution spectrograph became the tool of choice for this test, and the team observed another transit of K2-18b in 2024, enduring the typical delays and schedule changes that come with operating a telescope shared by astronomers around the world. The MIRI data arrived in mid-2024, and when Madhusudan's group processed the spectrum, they saw what looked like absorption features at wavelengths consistent with DMS and DMDS. More importantly, combining the MIRI observations with their earlier NIRIS and NIRSpec data allowed them to fit atmospheric models across the full 0.8 to 12 micron wavelength range, and models including these sulfur compounds provided statistically better fits than models without them. Statistical significance became the central question, and the team's analysis suggested the detection reached 3 sigma confidence, meaning the probability of seeing this signal if no DMS or DMDS existed in the atmosphere was approximately 0.3%. Bayesian inference calculations that compared how well different atmospheric models explain the observations generally favoured scenarios including one or both of the sulfur molecules, and when the team tested dozens of potential molecular candidates, DMS and DMDS consistently ranked among the species most likely to explain the observed spectral features. The phrase 99.7% confidence comes directly from this 3 sigma threshold, and understanding what this number means requires some statistical background. Astronomers typically assume measurement uncertainties follow a Gaussian or normal distribution, the classic bell curve shape where most measurements cluster near the true value and fewer measurements land farther away. 1 sigma represents the standard deviation of this distribution, and roughly 68% of measurements fall within 1 sigma of the average. 2 sigma captures about 95% of the distribution, 3 sigma includes 99.7%, and 5 sigma encompasses 99.9997%. Scientists in different fields use different significance thresholds before declaring a detection confirmed, and particle physicists, burned by numerous historical false positives, adopted a stringent 5 sigma standard decades ago that says if your result exceeds 5 standard deviations from what random chance would predict, you can claim a discovery. Gravitational wave detectors use similar thresholds, and the announced detection of gravitational waves from merging black holes in 2015 met the 5 sigma bar. Medical research typically uses lower thresholds, often accepting results at the 2 sigma or 95% confidence level, which makes sense given the practical impossibility of achieving 5 sigma certainty in clinical trials with limited sample sizes. Astronomy occupies middle ground, and while 5 sigma remains the gold standard for major discoveries, 3 sigma detections appear frequently in the literature as tentative findings worthy of follow-up. The distinction matters enormously, because a 3 sigma detection carries a 1 in 370 chance of being a statistical fluke, which sounds small but becomes worrying when you consider how many measurements astronomers make and how many opportunities exist for false positives. If you run 370 independent tests at 3 sigma significance, random chance predicts one of them will appear positive even if nothing real is there. The Cambridge team's approach involved fitting multiple atmospheric models to their combined spectroscopic data and using Bayesian statistics to determine which models best explain the observations. Bayesian analysis differs from classical statistical hypothesis testing by calculating the relative probabilities of different models given the data, and it naturally incorporates prior knowledge about how likely different scenarios are before considering the new observations. The team's paper presents Bayesian evidence ratios showing that models including DMS or DMDS are preferred over simpler models that exclude these molecules, though the preference is moderate rather than overwhelming. Critics immediately pounced on several weaknesses in this analysis, starting with the fundamental question of whether the MERI data actually contain real spectral features, or whether instrumental systematics created the appearance of absorption where none exists. Michael Radica at the University of Montreal led a reanalysis effort that independently processed the raw MERI data using different pipeline software, and found that the extracted planet spectrum changed substantially depending on which wavelength binning scheme they applied when combining individual detector pixels into spectral channels. The MERI detector produces data at very high spectral resolution, essentially sampling the spectrum at thousands of individual wavelengths, but the faint signal from the planet transmission spectrum requires binning these high-resolution measurements into broader wavelength channels to build up sufficient signal-to-noise ratio. The choice of how wide to make these bins and where to place their boundaries can significantly affect the final spectrum. And Radica's team demonstrated that most binning schemes they tested produced spectra inconsistent with strong absorption features at the wavelengths where DMS and DMDS absorb. The statistical test came down to comparing two competing hypotheses, one where the spectrum contains real absorption features, and another where the spectrum is essentially flat with no significant molecular signatures. Flat spectra arise when clouds or hazes in the atmosphere scatter light at all wavelengths equally, masking any underlying molecular absorption, and many exoplanet observations show such featureless spectra. Radica's analysis found that 5 out of 6 statistical tests they performed actually preferred the flat spectrum model over models with molecular features, and even when they specifically looked for Gaussian-shaped absorption lines at the expected positions of DMS and DMDS, the preference was weak, around 2 sigma rather than 3 sigma. Kevin Stevenson at Johns Hopkins University led another independent analysis published in August 2025 that reached even more damning conclusions, and his team applied multiple data reduction techniques to the MERI observations and concluded that unresolved systematic errors plague the mid-infrared data. The key issue involves what astronomers call red noise, systematic correlations in the data that aren't properly accounted for in standard error estimates, and red noise makes signals appear more statistically significant than they actually are, because the measurements aren't truly independent of each other. Stevenson's team found that different binning schemes applied to the MERI data produced wildly inconsistent transmission spectra, which they describe as a potpourri of shapes that then led to completely different atmospheric interpretations. When they used their preferred binning scheme, 87.5% of their model fits found no significant evidence for DMS or DMDS, and the molecules that did show up in their retrievals included ethane instead, a simple hydrocarbon that's chemically similar to DMS but formed through completely different processes. The interchangeability between DMS and ethane in explaining the data suggests the spectral features lack the uniqueness needed to confidently identify which molecule is actually present. The tension between near-infrared and mid-infrared data adds another layer of concern, and Stevenson's analysis noted that the MERI observations appeared to show large spectral features that should also produce detectable signals in the nearest and near-spec wavelength ranges, but the near-infrared data showed only modest features that don't quite match up in amplitude. This inconsistency suggests something other than atmospheric molecules might be creating apparent absorption in one wavelength range but not the other, pointing toward instrumental effects rather than astrophysical signals. Sarah Seeger at MIT, one of the pioneers of exoplanet atmosphere characterization, cautioned in interviews that the field has seen similar claims before that didn't hold up under scrutiny, and she specifically cited the 2019 detection of water vapor in K2-18b's atmosphere using Hubble data, which subsequent analyses cast doubt upon. The pattern of initial excitement followed by skepticism and eventual clarification or refutation has repeated multiple times in exoplanet science, and Seeger emphasized that patience and independent confirmation should precede any definitive claims about detecting signs of life. The chemical argument against the DMS detection centers on the absence of other molecules that should accompany sulfur compounds if they're really there, and ethane provides the clearest example. Ultraviolet radiation from K2-18's star should break apart any DMS or DMDS molecules in the upper atmosphere through a process called photodissociation, and the resulting molecular fragments, mainly methyl radicals, would recombine to form ethane along with other simple hydrocarbons. Photochemical models predict substantial ethane abundances if DMS or DMDS exist at the concentrations claimed, yet the Webb observations show no convincing ethone detection. Eddie Schwieterman at UC Riverside pointed out this discrepancy in press interviews, noting that the absence of expected photochemical byproducts makes him skeptical the sulfur compounds are present at all. Either the atmospheric models incorrectly predict ethane formation, which would undermine confidence in all our photochemical calculations for exoplanet atmospheres, or the DMS and DMDS aren't actually there, and some other explanation accounts for the spectral features. Neither option provides much comfort for the biosignature interpretation. Spectroscopic ambiguity poses yet another problem, and the researchers themselves acknowledged in their paper that DMS and DMDS have very similar absorption spectra in the wavelength ranges Webb observed, making it difficult to distinguish between the two molecules or determine whether both are present. Many other organic molecules containing methyl groups show absorption features in the same regions, and without higher spectral resolution or additional wavelength coverage, definitively identifying which compound produces the observed signal remains challenging. The possibility of abiotic DMS production received a major boost in 2024 when astronomers reported detecting dimethyl sulfide in a comet, an environment where biological processes almost certainly don't operate. Nora Haney at the University of Bern announced the discovery at a European Geosciences conference, explaining that her team found DMS in the coma of Comet 67P Churyumov-Gerasimenko, using data from the Rosetta spacecraft, which orbited the comet from 2014 to 2016. Comets contain pristine material left over from the solar system's formation, and the presence of DMS on such a cold, lifeless object demonstrated that non-biological chemistry can manufacture this supposedly biological molecule. The detection was controversial, and some researchers questioned whether the Rosetta instruments actually measured DMS or confused it with other sulfur-bearing molecules, but subsequent analyses supported Haney's interpretation, and independent detections of DMS in the interstellar medium through radiotelescope observations provided additional evidence that abiotic synthesis pathways exist. The mechanisms remain unclear, but possibilities include UV-driven photochemistry acting on simpler sulfur compounds or reactions occurring on the surfaces of ice grains in cold environments where molecules can stick and interact over extended timescales. The concentration argument cuts both ways in this debate, and the Cambridge team notes that K2-18b's atmosphere apparently contains DMS, or DMDS, at levels thousands of times higher than Earth's, which they argue makes abiotic production implausible because known non-biological pathways produce only trace amounts. Critics respond that we simply don't know enough about chemistry under the conditions present on K2-18b to make confident predictions about what's possible, and extraordinary planetary environments might enable reaction pathways that don't operate on Earth or in the cold vacuum of interstellar space. The scientific controversy recalls previous episodes where promising biosignature detections fell apart under closer scrutiny, and the phosphine on Venus saga from 2020 provides the most relevant cautionary tale. Jane Greaves at Cardiff University and her colleagues announced they detected phosphine in Venus's atmosphere using ground-based radio telescopes, and phosphine seemed like an ideal biosignature because on Earth it's produced mainly by anaerobic microorganisms in oxygen-poor environments. The detection sparked tremendous excitement about the possibility of microbes living in Venus's cloud layers, which offer relatively temperate conditions compared to the hellish 460-degree surface. Within months, independent teams reanalyzed the same telescope data and found major problems with the original detection, including systematic errors in data processing and possible confusion between phosphine's spectral signature and that of sulfur dioxide, which exists in Venus's atmosphere in vast quantities. Follow-up observations using different telescopes sometimes supported the detection and sometimes contradicted it, and the scientific consensus eventually shifted towards skepticism though the question isn't entirely settled. The key lesson involves recognizing that extraordinary claims require extraordinary evidence, and faint signals at the edge of detectability need independent confirmation from multiple techniques before acceptance. The Mars meteorite controversy from 1996 demonstrates how even physical samples can mislead scientists searching for signs of life. And when David McKay's team at NASA announced evidence of fossilized bacteria in the Martian meteorite ALHE 4001, including distinctive teardrop-shaped magnetite crystals that looked biological, the finding generated worldwide headlines. President Clinton gave a speech celebrating the possible discovery of ancient Martian life, and the public's imagination ran wild with implications for how common life might be in the universe. Subsequent research revealed that magnetite crystals resembling the supposedly biological ones could form through purely inorganic processes at high temperatures, and other features interpreted as fossil remains, including carbonate globules and organic molecules, also had plausible non-biological origins. The initial excitement gave way to skepticism, as researchers demonstrated that the evidence didn't uniquely point to biology, and today most scientists regard the meteorite findings as inconclusive at best, and more likely the result of abiotic Martian geology. These examples don't mean the K2-18b detection is wrong, but they illustrate why the astronomical community maintains healthy skepticism toward claimed biosignatures, and the burden of proof sits heavily on researchers proposing we've found life rather than on skeptics demanding more evidence. Carl Sagan popularized the phrase, "Extraordinary claims require extraordinary evidence," and claiming we've detected signs of extraterrestrial life for the first time in human history qualifies as about as extraordinary as claims get. The Cambridge team has expressed appropriate caution even while championing their findings, and Madhusudan emphasized in press releases and interviews that they view their results as a starting point for further investigation rather than a definitive detection. He acknowledged the possibility of unknown abiotic chemistry, and stressed the need for additional observations to reach 5 sigma confidence before claiming a biosignature discovery. The team calculated that roughly 16 to 24 hours of additional GeoST observation time would be needed to achieve 5 sigma significance, assuming the signal is real and not an artifact. Securing that much telescope time for a single target represents a major challenge given Webb's status as a heavily oversubscribed facility where demand far exceeds available observing hours, and the competition for time is fierce, with success rates typically below 20% for proposed observations. The Telescope Allocation Committee would need to decide whether pursuing this target justifies the opportunity cost of not observing other objects, and that decision depends partly on the committee's assessment of whether the initial 3 sigma detection is credible enough to warrant the investment. NASA's public stance on the finding reflects institutional caution about overhyping results before they're confirmed, and while the space agency issued press releases for previous JWST observations of K2-18b, they declined to do so for the 2025 paper claiming DMS and DMDS detection. A NASA statement to the Washington Post emphasized that detecting a single potential biosignature would not constitute discovery of life, and the agency stressed that multiple independent lines of evidence are needed before making such an extraordinary claim. The statement aligns with standard protocols established by the astrobiology community for evaluating potential biosignatures and a framework published by NASA's Nexus for Exoplanet System. Science lays out several questions that must be answered before accepting evidence as indicating life. First, have we detected an authentic signal rather than instrumental noise, which is precisely the question independent analyses are now contesting. Second, assuming the signal is real, can we confidently identify which molecule produced it, rather than confusing it with other compounds? Third, does the identified molecule actually indicate biological activity, or could abiotic processes explain it equally well? Fourth, if we can't rule out abiotic explanations, does the environmental context make biological production more likely than non-biological alternatives? Fifth, can we obtain multiple independent pieces of evidence that all point toward the same conclusion rather than relying on a single ambiguous signal? K2-18b arguably passes the first 3 tests according to the Cambridge team's analysis, though critics dispute whether the signal is authentic and whether the molecular identification is secure. The 4th and 5th questions remain largely unanswered, and this is where future observations would need to focus. Additional observations could take multiple forms beyond simply spending more time staring at K2-18b with MIRI, and the most powerful approach would involve observing the planet with completely independent instruments on different telescopes. The European Space Agency's Ariel mission, scheduled to launch in 2029, will specialise in exoplanet atmosphere characterisation and could potentially re-observe K2-18b using different spectroscopic techniques. NASA's Nancy Grace Roman Space Telescope, launching around the same time, might also contribute observations, though its primary science goals lie elsewhere. Higher spectral resolution represents another avenue for strengthening the detection, and while MIRI's low-resolution spectrograph adequately sampled the broad absorption features expected from DMS and DMDS, fine structure within those features could provide more definitive molecular identification. Future spectrographs on extremely large ground-based telescopes, machines with primary mirrors 30 or 40 meters in diameter, compared to Webb's 6.5 meters, will achieve spectral resolutions hundreds of times better than current space-based instruments, though they'll need to contend with Earth's atmosphere complicating observations. The search for complementary biosignatures offers perhaps the most promising path forward, and detecting multiple molecules that on Earth arise from biology would dramatically strengthen the case compared to finding a single ambiguous compound. Oxygen provides the gold standard biosignature that astrobiologists have dreamed about detecting, though K2-18b's hydrogen-rich atmosphere probably lacks substantial oxygen even if life exists there, because oxygen would rapidly react with hydrogen and vanish. Other possibilities include methyl chloride, ammonia in unexpected abundances, or organic compounds like acetylene and ethylene that simple metabolisms produce. The question of what we might actually be detecting if life exists on K2-18b deserves consideration, and nobody suggests anything resembling fish or whales swimming through alien oceans, nor even larger multicellular organisms like kelp or coral. The most plausible scenario involves microbial life comparable to Earth's simplest single-celled organisms, probably occupying niches in the water column where conditions support basic metabolism. Marine phytoplankton on Earth exist as single cells or colonies of cells that drift with ocean currents, and they dominate the upper sunlit layers of the ocean where photosynthesis can occur. Whether photosynthesis as we understand it could function on K2-18b remains questionable, given the planet's hydrogen atmosphere, which would dramatically alter the spectrum of light reaching the surface compared to Earth's nitrogen-oxygen atmosphere. Red dwarf stars like K2-18 emit most of their energy in the red and near-infrared part of the spectrum, rather than the visible light our eyes are adapted to see, and this shifts the optimal wavelengths for photosynthesis away from the green and blue light that Earth plants use. Organisms would need different photosynthetic pigments tuned to harvest the available light, and whether biochemistry can evolve such pigments represents an open question. Alternative metabolisms not based on photosynthesis might dominate on a Hycean world, and Earth hosts numerous organisms that derive energy from chemical reactions rather than sunlight. Chemosynthetic bacteria at hydrothermal vents harvest energy from the reaction between hydrogen sulfide and oxygen, while methanogens produce methane by combining hydrogen with carbon dioxide. A hydrogen-rich atmosphere provides abundant fuel for hydrogen-based metabolisms, and microorganisms could potentially thrive throughout the ocean column, rather than being confined to the sunlit surface layers. The sheer abundance of life needed to produce detectable atmospheric signatures requires populations orders of magnitude larger than individual colonies, and Earth's oceans contain roughly 1 million bacteria per milliliter of seawater in typical conditions, which adds up to roughly 1 nonillion bacteria in the entire ocean. This vast population produces enough DMS to create measurable concentrations in the atmosphere, but the rate of production and removal must balance carefully to maintain steady-state abundances. K2-18b would need similarly productive oceans or even more prolific life to generate the high DMS concentrations apparently detected, assuming the molecule really is there. The timescale for life to arise and become widespread enough to create biosignature gases remains deeply uncertain, and Earth's history provides exactly one example to draw from. Life appeared on our planet relatively quickly, within the first few 100 million years after the surface cooled enough for liquid water to exist, but it remained microscopic and limited in scope for the vast majority of Earth's history. complex multicellular life only emerged around 600 million years ago, while humans showed up within the last few 100,000 years, meaning we represent a tiny fraction of Earth's biological history. K2-18's age has been estimated at roughly 2.4 billion years, substantially younger than our Sun's 4.6 billion years, but potentially old enough for life to have arisen and evolved if conditions were suitable. The planet itself presumably formed around the same time as its star, though planets can migrate inward or outward from their formation locations, and K2-18b's current position in the habitable zone might not be where it originated. Whether the planet maintained habitable conditions throughout its history, or experienced periods of extreme heat or cold that would sterilize any emerging life, remains unknown. Stellar activity poses another challenge for habitability around red dwarfs, and these small stars produce powerful flares that can temporarily increase their luminosity by factors of 10 or more in just minutes. The flares emit intense ultraviolet and X-ray radiation that would bombard any nearby planet, potentially stripping away atmospheric gases and damaging organic molecules on the surface. Young red dwarfs flare much more frequently than older ones, and K2-18 displays moderate activity levels that fall somewhere in the middle of the spectrum, observed for stars of its type. The protective effect of a thick hydrogen atmosphere might shield surface life from the worst effects of stellar radiation, though hydrogen itself provides little shielding from high-energy photons compared to nitrogen and oxygen. Water vapor in the atmosphere could help absorb ultraviolet light, and if the planet has a magnetic field generated by a liquid iron core, magnetic shielding would deflect charged particles from stellar flares the way Earth's magnetosphere protects us from the solar wind. No observations have detected a magnetic field on K2-18b, but current instruments can't detect exoplanet magnetic fields except in special cases like hot Jupiters, orbiting very close to their stars. Assuming for the moment that K2-18b does harbour life, and the detected DMS or DMDS genuinely comes from biological activity, the implications would revolutionise astrobiology and our understanding of our place in the cosmos. The discovery would immediately elevate Hycean worlds to premier targets for future life-hunting missions, and would suggest that habitable conditions exist on a much wider variety of planets than Earth-like rocky worlds alone. The sheer number of Hycean candidates identified in surveys of nearby stars would multiply the estimates of potentially inhabited worlds in our galaxy, and the implications would ripple through multiple scientific disciplines from planetary science to evolutionary biology to the philosophy of science itself. Consider what confirming life on K2-18b would mean for our understanding of biochemistry and the requirements for life. Earth's biochemistry relies on specific conditions including liquid water, moderate temperatures, and a particular range of chemical elements in available forms. But if life emerged independently on a Hycean world with dramatically different conditions, it would demonstrate that the viable parameter space for life extends far beyond what we observe on Earth. The hydrogen-rich atmosphere alone represents an extreme departure from Earth's oxidizing environment. Yet if organisms thrive under such conditions, it suggests that biochemistry is far more flexible and adaptable than many scientists currently believe. The discovery would also force reconsideration of how common technological civilizations might be in the galaxy, though the connection requires careful reasoning, because detecting microbes doesn't directly tell us about the likelihood of intelligence evolving. Earth's own history shows that life remained microbial for roughly 3 billion years before multicellular organisms appeared, and even after that transition, intelligence capable of building technology took another 600 million years to develop. If K2-18b harbours life that's been around for 1 billion years or more but remains microbial, it would support the hypothesis that while simple life might arise readily, complex life and intelligence represent much rarer achievements requiring additional improbable steps. Conversely, if we eventually discovered that K2-18b's oceans contained not just microbes, but diverse ecosystems with varying levels of complexity, it would suggest that given enough time, life naturally tends toward increasing complexity and diversity. The ocean environment on a Hycean world might actually promote the evolution of complex organisms because the global nature of the ocean eliminates many of the barriers and geographic isolation events that drove speciation on Earth, though it could also limit complexity by preventing the extreme environmental variations that sometimes spur evolutionary innovation. The philosophical implications extend beyond just confirming that we're not alone, because the question of whether life is common or rare fundamentally shapes how we view ourselves and our responsibilities as the only known technological species in our corner of the universe. If life turns out to be abundant, with microbial ecosystems thriving on countless Hycean worlds and rocky planets throughout the galaxy, then our emergence represents just one instance of a common phenomenon, and the probability of other intelligent species existing somewhere among the billions of habitable planets becomes quite high, even if the step from simple to complex to intelligent life remains difficult. On the other hand, if extensive surveys reveal that life is actually quite rare, with K2b being one of only a handful of inhabited worlds within hundreds or thousands of light years, then Earth's biosphere takes on special significance as an unusual and precious occurrence. The responsibility to preserve Earth's life and potentially spread it to other worlds becomes more pressing if we're truly among the only living systems in our region of space, and the Fermi paradox, which asks why we haven't detected any signs of advanced civilizations despite the apparent high probability of their existence, might find partial resolution in life being much rarer than optimistic projections suggest. The sociological and psychological impact of confirmed extraterrestrial life cannot be overstated, even if that life consists of nothing more exciting than bacterial mats floating in alien oceans. Humanity has speculated about life beyond Earth for millennia, and finding definitive proof would mark a turning point in our species' understanding of its place in the cosmos, comparable to the Copernican revolution or Darwin's theory of evolution. Every human culture and religion would need to grapple with the implications, and while some theological traditions have already developed frameworks for accommodating extraterrestrial life, others would face challenges reconciling the discovery with their cosmological worldviews. The practical scientific benefits of confirming life on K2-18b would be enormous, even independent of the philosophical significance, because it would provide our first opportunity to study biochemistry that evolved entirely separately from Earth's biosphere. Comparing the two systems would reveal which features are universal constraints on all biochemistry versus which represent contingent historical accidents specific to Earth's particular evolutionary path. Do all biochemistries use something analogous to DNA for information storage? Or does Earth's choice of nucleic acids represent just one solution among many possibilities? Do all cells require lipid membranes to maintain internal homeostasis, or might other boundary structures work equally well? The metabolism question becomes particularly interesting in this context, because Earth life has evolved an astonishing diversity of metabolic strategies for extracting energy from the environment, yet all share certain common features, including the use of phosphate bonds to store and transfer energy. If K2-18b's organisms use completely different energy currency molecules or novel metabolic pathways unknown on Earth, it would expand our understanding of what's biochemically possible, and might even suggest new approaches for industrial chemistry or biotechnology applications. Astrobiology would transform overnight from a largely theoretical discipline into an observational science with 2 data points to compare instead of just one, and the addition of even one more example of life would dramatically improve our ability to distinguish universal principles from local contingencies. With only Earth to study, we can't tell whether features we observe are necessary consequences of chemistry and physics, or just accidents of our particular origin, but comparing Earth life to K2-18b life would begin illuminating which characteristics represent fundamental requirements and which are evolutionary happenstance. The discovery would also galvanize public interest in space exploration and scientific research more broadly, potentially leading to increased funding for astrobiology, planetary science, and related fields. Major scientific breakthroughs often capture public imagination in ways that generate lasting increases in support for research, and finding life beyond Earth would rank among the most significant discoveries in human history, comparable in impact to the discovery of DNA's structure or the development of quantum mechanics. The political will to fund ambitious space missions tends to wax and wane, but confirming extraterrestrial life could create sustained enthusiasm for exploring the cosmos and searching for additional examples of living systems. Educational systems would need to incorporate the discovery into curricula across multiple subjects from biology to chemistry to philosophy, and textbooks would require revision to reflect the new understanding of life's place in the universe. Students growing up after such a discovery would have fundamentally different baseline assumptions about cosmological questions than previous generations did, and this shift in worldview could influence career choices, research priorities, and cultural attitudes towards science and exploration. The religious dimensions of confirming extraterrestrial life deserve thoughtful consideration rather than dismissal, because billions of people draw meaning and moral guidance from religious traditions, and the discovery would inevitably prompt theological reflection and potentially revision of some doctrines. Many religious thinkers have already concluded that nothing in their traditions precludes life existing elsewhere, and some argue that a creator capable of producing one living world could certainly produce many, making the existence of extraterrestrial life entirely compatible with, and perhaps even expected by, theistic worldviews. Others might face more difficulty reconciling the discovery with specific scriptural passages or theological concepts that assume humanity's unique status in creation, though religious traditions have historically demonstrated considerable flexibility in reinterpreting texts and doctrines in light of new scientific discoveries. The Catholic Church's eventual acceptance of heliocentrism and evolution, despite initial resistance, demonstrates that religious institutions can adapt to scientific findings that initially seem challenging to traditional teachings. The interfaith dialogue that would inevitably follow such a discovery might itself prove valuable, prompting different traditions to engage seriously with each other's perspectives on humanity's place in a cosmos that contains other living systems. Some traditions emphasize humanity's special relationship with the divine, while others take a more cosmic perspective that could more easily accommodate extraterrestrial life, and comparing these different approaches might yield insights relevant even to people who don't identify with any particular religious tradition. The practical question of whether and how we should attempt communication with life on K2-18b becomes relevant even though microbial life cannot respond to messages, because confirming life there would make systematic searches for technological civilizations in that system more appealing. While microbes can't build radio telescopes, the presence of life increases the probability that the system harbours more complex organisms or might develop technological intelligence given enough time, and this could influence decisions about whether to target K2-18's stellar system with focused searches for artificial signals. The SETI community, which has searched for signals from extraterrestrial intelligence for decades without success, would likely view the discovery as validation of their efforts and motivation to continue, because finding even microbial life would dramatically strengthen the case that intelligence might arise elsewhere. The probability calculations that underlie SETI's search strategies depend critically on estimates of how often life emerges on habitable planets, and confirming life on K2-18b would shift those probabilities in favour of intelligence being less rare than some pessimistic scenarios suggest. The planetary protection implications also matter more than casual observers might realise, because international treaties and scientific protocols govern how we conduct space exploration to minimise the risk of contaminating other worlds with Earth life or bringing alien organisms back to Earth. If K2-18b does harbour life, the planet would immediately be classified as a special region under planetary protection protocols, even though it sits 124 light-years away, and we have no capability to send spacecraft there with current technology. The philosophical discussion would expand to include questions about the moral status of alien life, and whether we have ethical obligations toward extraterrestrial organisms, even if they're just microbes. Earth's environmental movement established the principle that humans have responsibilities to protect ecosystems and species on our planet, and confirming life elsewhere would raise questions about whether similar principles apply to alien ecosystems. Does microbial life on K2-18b have intrinsic value that we should respect? Or does its moral status depend on whether it might eventually evolve into more complex forms? The theological concept of stewardship, present in many religious traditions, would gain new dimensions if we confirm that life exists beyond Earth, because it would expand the scope of potential human responsibility from just our planet to potentially all living systems we become capable of affecting. Even if we can't physically reach K2-18b, our broadcasts and signals travel through space at the speed of light, and powerful transmissions could theoretically be detected at interstellar distances, raising questions about whether we should be more thoughtful about what we send out into the cosmos. The scientific method itself would face interesting challenges from confirming life on K2-18b, because verifying biological origin of the detected molecules would require ruling out all plausible abiotic explanations, and our understanding of chemistry under extreme conditions remains incomplete enough that new, non-biological pathways could always be proposed. The demarcation between what counts as sufficient evidence for life versus what leaves room for doubt involves judgment calls that different scientists will answer differently based on their background assumptions and tolerance for uncertainty. The discovery would also accelerate development of the conceptual and methodological tools needed for studying life in general, rather than just Earth life specifically, and astrobiology would mature into a more rigorous discipline with clear empirical foundations rather than remaining largely speculative. The field would need to develop standardized approaches for characterizing alien biochemistry, establishing whether detected organisms share a common origin or rose independently, and determining how to classify and study living systems that might operate on fundamentally different principles than Earth life. Drake's equation provides a framework for estimating how many technological civilizations might exist in the Milky Way, and while highly speculative, the equation breaks down the problem into a series of factors, including the rate of star formation, the fraction of stars with planets, the number of habitable planets per star system, the fraction of habitable planets where life arises, and so on. Most uncertainty lies in the last few factors, particularly the probability that life emerges once habitable conditions exist, and the fraction of life-bearing worlds that develop intelligence and technology. Confirming life on K2-18b wouldn't directly answer whether technological civilizations exist, since we're talking about microbes rather than anything capable of building radio telescopes, but it would strongly suggest that life arises readily given suitable conditions. If life emerged independently on both Earth and K2-18b, and these are the only two locations we've thoroughly searched, the implication would be that life represents a common outcome rather than a fantastically improbable fluke. This would shift the Drake equation parameters in favour of abundant life throughout the galaxy, though whether that life ever becomes complex or intelligent remains a separate question. The negative scenario, where additional observations falsify the biosignature detection, also carries important lessons for the field, and demonstrating that what appeared to be signs of life actually resulted from instrumental artifacts or misinterpreted data would teach researchers valuable lessons about the limits of current technology and analysis techniques. The controversy has already pushed the community to develop more rigorous standards for evaluating biosignature claims and highlighted the need for independent confirmation before public announcements. Future missions specifically designed to characterize terrestrial exoplanet atmospheres would benefit from the K2-18b experience, regardless of how the current debate resolves, and NASA's Habitable Worlds Observatory, still in the planning stages for launch in the 2040s, aims to directly image dozens of potentially habitable planets and take detailed spectra of their atmospheres. Learning what does and doesn't constitute compelling evidence for biosignatures now, while we're working with the first generation of instruments capable of attempting such detections, will inform the design of future telescopes optimized for this science. The larger context involves recognizing that finding life beyond Earth represents one of the most profound questions humans can ask, and rushing to claim success before the evidence justifies it risks damaging public trust in science, while also potentially missing the real discovery when it does happen. The history of science contains numerous examples of premature claims that later proved incorrect, and these episodes often generate more skepticism and cynicism than would have resulted from maintaining appropriate caution until the evidence became conclusive. K2-18b will remain under intense scrutiny for years to come, and multiple research teams have already proposed additional observations using various telescopes and techniques. The planet sits in a relatively favourable position for detailed study because its 124 light-year distance makes it close enough that we can collect sufficient photons for high-quality spectra, while its red dwarf host star is bright enough to observe but dim enough that the planet's atmospheric signal doesn't get completely swamped by stellar noise. The 33-day orbital period strikes a balance between being short enough for frequent observations but long enough that transits don't occur so often that they're hard to schedule. Other potentially habitable planets offer different trade-offs, and some targets lie closer to Earth but orbit fainter stars requiring longer exposure times, while others have favourable stellar properties but sit farther away so fewer photons reach our telescopes. The recently discovered planet TOI 270d orbits a similar red dwarf star about 70 light-years away, and has been proposed as another potential Hycean world, and early JWST observations showed evidence for water vapour and carbon dioxide in its atmosphere, though no biosignature molecules were reported. The TRAPPIST-1 system contains 7 Earth-sized planets, orbiting an ultra-cool red dwarf just 40 light-years away, and several of these planets sit in, or near, the habitable zone, though they're probably more like Mars than Earth given their small sizes and likely thin atmospheres. JWST has begun observing these planets, but hasn't reported any confirmed atmospheric detections yet, and the system remains a high-priority target for searching for signs of life on truly Earth-sized worlds, rather than larger sub-Neptunes like K2-18b. Proxima Centauri b holds special significance as the closest known exoplanet to Earth, orbiting a red dwarf just 4 light-years away, but its proximity comes with challenges because Proxima Centauri is one of the most active stars known, bombarding the planet with radiation that probably stripped away any atmosphere long ago. Even if Proxima b had an atmosphere, detecting it would prove difficult because the star's variability creates noise that obscures the subtle signals we're looking for. The statistical reality of biosignature searches involves acknowledging that most planets we examine probably won't show signs of life, even if life turns out to be common in the universe, and this is because detecting biosignatures requires not just that life exists, but that it exists at high enough concentrations to alter atmospheric chemistry in observable ways. Earth went through billions of years where life existed but wouldn't have been detectable from interstellar distances because oxygen levels remained too low to create a strong spectral signature. This observation window problem means we might survey hundreds or thousands of planets before finding one where life has become abundant enough and developed the right chemistry to produce detectable gases, and even then, we need to be lucky enough to catch the planet at a stage in its evolution where the biosignature-producing organisms dominate. K2-18b might represent exactly this kind of favourable case, or it might be a false alarm and we likely won't know which until significantly more data accumulates. The scientific method demands reproducibility and independent verification, and in the case of K2-18b, this means other teams using different instruments and analysis techniques need to confirm or refute the Cambridge Group's findings. The fact that multiple independent analyses of the same JWST data have reached contradictory conclusions suggests the signal sits right at the edge of what current technology can reliably measure. And this borderline status means we need either better data from longer observations, or completely independent observations from different telescopes to break the tie. The debate also highlights how different scientists can look at the same evidence and draw different conclusions based on their prior beliefs about how likely different scenarios are. And this is where Bayesian reasoning comes in, because Bayesian statistics explicitly incorporates prior probability assessments into the analysis. A researcher who believes Hycean worlds are rare and biosignatures unlikely will naturally assign lower prior probability to models including DMS, which means they'll demand stronger evidence before accepting the detection. Conversely, a researcher who thinks life should be common might assign higher prior probability to biological explanations and accept weaker evidence. Neither approach is wrong in principle, but they can lead to different conclusions about whether the current data sufficiently supports the biosignature interpretation, and this philosophical difference underlies much of the disagreement between proponents and skeptics of the detection. The resolution will likely come from accumulating enough data that the evidence becomes overwhelming regardless of what prior probabilities different scientists assign, and reaching this point typically requires achieving 5 sigma significance, where the signal is so strong that even the most skeptical prior beliefs have to shift. The K2-18b story reminds us that science works through incremental progress rather than sudden revolutionary breakthroughs, and while the public tends to hear about research when major announcements hit the news, most scientific progress happens through gradual accumulation of evidence, testing of hypotheses, and refinement of theories. The current 3 sigma detection represents an important step in that process, even if it eventually turns out to be a false positive, because it's pushing the boundaries of what we can measure and revealing the challenges we'll need to overcome to make definitive biosignature detections. The technology continues improving, and the instruments available for exoplanet characterization today vastly exceed what existed even 10 years ago. While the instruments under development for the 2030s and 2040s will make Webb's capabilities look primitive, The Nancy Grace Roman Space Telescope will carry a coronagraph that can block starlight and image planets directly, rather than relying solely on transit spectroscopy, opening new pathways for atmospheric studies, and this direct imaging capability allows astronomers to observe planets at any point in their orbit, rather than waiting for transits. Though it works best for large planets far from their stars where the contrast ratio between planet and star is more favourable. The European Extremely Large Telescope with its 39-metre primary mirror will achieve spectral resolution roughly 100 times better than Webb, allowing identification of individual molecular absorption lines rather than broad features. And this high-resolution spectroscopy will resolve ambiguities that plague current observations by clearly separating overlapping spectral features from different molecules. Ground-based telescopes face the disadvantage of observing through Earth's atmosphere, which absorbs many infrared wavelengths and introduces seeing effects that blur images. But adaptive optic systems that measure and correct for atmospheric turbulence in real time have advanced to the point where ground telescopes can achieve image quality, rivaling space telescopes for many applications. The next generation of space telescopes after Webb and Roman will likely include missions specifically optimized for characterizing terrestrial exoplanet atmospheres, and these instruments will combine large collecting areas for maximum sensitivity with advanced coronagraphs or starshades to suppress stellar glare and high-resolution spectrographs capable of dissecting atmospheric spectra in unprecedented detail. NASA's planned Habitable Worlds Observatory remains in early conceptual stages, but envisions a telescope potentially larger than Webb, specifically designed to image and spectroscopically characterize dozens of Earth-like exoplanets in the habitable zones of nearby stars, and securing funding for such an ambitious mission will require sustained political support and public interest in the search for life beyond Earth. Starshade technology represents one of the most promising approaches for achieving the extreme contrast ratios needed to image Earth-sized planets around Sun-like stars, and a starshade is essentially a giant flower-shaped screen positioned tens of thousands of kilometers in front of a space telescope to block starlight, while allowing light from planets to pass around its specially designed edges. The engineering challenges are enormous, requiring precision formation flying to maintain alignment between the starshade and telescope to within meters, while both move through space. But multiple NASA-funded studies have demonstrated the concept's feasibility, and a starshade mission could launch in the 2030s to work with Roman or a follow-on telescope. Ground-based telescopes also continue advancing, and the next generation of extremely large telescopes under construction includes the 30-meter telescope, the Giant Magellan Telescope, and the European Extremely Large Telescope, all scheduled to begin operations in the early 2030s, and these facilities will work alongside space telescopes, providing complementary observations at wavelengths where Earth's atmosphere is transparent and offering the flexibility to respond quickly to new discoveries or sudden events like stellar flares that might affect observations of K2-18b or similar targets. The theoretical and computational side of the field is advancing just as rapidly as observational capabilities, and researchers are developing increasingly sophisticated models of exoplanet atmospheres that account for complex chemistry, cloud formation, atmospheric circulation, and the intricate interplay between radiation and matter. And these models help interpret observations by predicting what spectral signatures different atmospheric compositions should produce. And they also guide observers by identifying which molecules are most likely to serve as reliable biosignatures under various planetary conditions, while revealing potential false positives that could mimic biological signals. Laboratory experiments complement theoretical work by measuring the physical and chemical properties of relevant molecules under conditions relevant to exoplanet atmospheres, and researchers create these conditions in vacuum chambers, high-pressure cells, and specialized spectroscopy setups that simulate the temperatures and pressures found on distant worlds. The spectroscopic databases that astronomers rely on to interpret telescope observations all derive ultimately from laboratory measurements. And improving the accuracy and completeness of these databases directly translates into better atmospheric characterizations, which is why multiple international teams continue measuring absorption, cross-sections, and line strengths for molecules of astrobiological interest. Machine learning and artificial intelligence are increasingly being deployed to help analyze exoplanet data, and neural networks can learn to recognize subtle patterns in spectroscopic data that traditional analysis methods might miss. while also helping to distinguish real signals from instrumental artifacts by training on large data sets that include both genuine detections and known false positives. AI systems are also being used to optimize observing strategies, determining which targets to observe and for how long to maximize the scientific return given limited telescope time. And some research groups have begun experimenting with automated discovery pipelines that can identify interesting planets in survey data without requiring human scientists to examine every potential candidate individually. The data analysis challenges shouldn't be underestimated, because modern astronomical instruments produce torrents of information that overwhelm traditional processing methods, and the raw data from a single JWST observation can fill terabytes of storage, requiring sophisticated reduction pipelines to extract scientifically useful spectra from the noise and systematic effects inherent in any real instrument. Different research teams often develop their own independent pipelines, using different assumptions and methods, which is why we sometimes see contradictory results from analyses of the same dataset. And this diversity of approaches represents a strength of the scientific process, because it helps reveal when conclusions depend sensitively on particular analysis choices that might not be justified. The human element remains crucial despite all the technological advances, and ultimately it takes careful scientists exercising sound judgment to interpret complex data and draw appropriate conclusions, and no algorithm or AI system can replace the deep understanding that comes from years of studying a particular scientific domain. The K2-18b controversy demonstrates the scientific process working as intended, with researchers proposing a provocative finding that others immediately scrutinize and test using independent methods, and the debate will continue until either the evidence becomes compelling enough to convince skeptics or alternative explanations prove more convincing to the detection's proponents, and this back and forth represents how science makes progress through vigorous but collegial debate. Whether K2-18b truly harbours life, or whether this detection proves to be a false alarm, the planet has already secured its place in astronomical history as the first exoplanet, where potential biosignatures were reported at statistically significant levels, though still below the confirmation threshold, and the intense scrutiny this claim has received will shape how future biosignature searches are conducted and reported. The lessons learned from this case will help the community develop better standards for evaluating evidence and communicating findings to both scientific peers and the public, and discussions are already underway about establishing clear guidelines for what constitutes sufficient evidence for a biosignature claim, and what level of peer review should precede public announcements of such extraordinary findings. The communication challenge facing scientists working on potentially life detection studies involves balancing the need for transparency and public engagement against the risk of generating misleading headlines that oversimplify or exaggerate the findings, and this tension plays out repeatedly as research groups navigate the fraught territory between making their work accessible to non-specialists and maintaining scientific rigour. The Cambridge team's decision to publish their findings in a peer-reviewed journal and hold a press conference reflects standard practice for significant results, but the framing of the discovery as 99.7% confidence in a potential biosignature perhaps invited more definitive interpretation than the actual strength of the evidence warranted. The role of science journalism in interpreting and communicating these findings to the public cannot be overlooked, because most people encounter scientific discoveries through news articles and social media rather than reading original research papers, and the quality of that secondary reporting varies enormously from careful nuanced coverage that captures the uncertainties to sensationalized headlines that promise more than the science delivers. Science communicators face the perpetual challenge of making complex technical topics accessible without sacrificing accuracy, and biosignature detection sits at the intersection of genuinely fascinating science and immense public interest, creating pressure to tell an exciting story that may not yet be fully supported by the data. The funding and policy implications of the K2-18b findings extend beyond just whether this particular detection proves real, because high-profile claims of potential biosignatures influence how governments and funding agencies prioritize different areas of research and how much money flows into astrobiology versus other scientific endeavours. A confirmed detection of life beyond Earth would almost certainly trigger increased investment in relevant technologies and missions, while a series of false alarms could generate skepticism that makes it harder to secure resources for continued searches. creating tension between scientists wanting to report interesting preliminary findings and the desire to avoid fatigue from overhyped claims that don't pan out. The international dimension of astrobiology research matters increasingly as multiple space agencies pursue complementary missions and capabilities, and while NASA leads in many areas of exoplanet science, the European Space Agency's contributions like the Ariel mission and international collaborations on ground-based telescopes ensure that the search for life proceeds through globally distributed efforts that don't depend on any single nation's continued commitment. This distributed approach provides resilience against the political and budgetary uncertainties that plague large-scale science projects, because if one agency's priorities shift, others can potentially fill gaps and maintain momentum. The educational opportunities presented by the search for life beyond Earth extend from inspiring the next generation of scientists to fostering scientific literacy among the general public, and stories like K2-18b capture people's imagination in ways that abstract discussions of spectroscopy and atmospheric chemistry never could, providing teachable moments for explaining how science works and why skepticism and demanding high standards of evidence are features rather than bugs of the scientific method. Students learning about this controversy can see firsthand how scientists debate, analyze data from multiple perspectives, and gradually converge on better understanding through open exchange of ideas and criticism. The philosophical questions raised by searching for life beyond Earth touch on fundamental issues of meaning, purpose, and humanity's place in the cosmos, and while science cannot answer whether life has intrinsic meaning or purpose, confirming that life exists elsewhere would reshape the context for those philosophical discussions by demonstrating that our existence represents one instance of a more general phenomenon rather than something utterly unique. Different philosophical traditions offer varying frameworks for thinking about our relationship to the universe and potential other life forms, from anthropocentric views that prioritize human interests to more egalitarian cosmopolitan perspectives that grant moral consideration to all entities capable of experiencing well-being. The long-term future of biosignature searches involves not just detecting life, but potentially characterizing its properties in enough detail to draw conclusions about evolutionary pathways, biochemical strategies, and possibly even geological or meteorological features of inhabited worlds. And each new observational capability opens possibilities for asking more detailed questions about planets that show signs of life. If we progress from detecting simple biosignature molecules to identifying seasonal variations in atmospheric chemistry that suggest biological cycles, or finding combinations of gases that indicate metabolic activity, our understanding of how life operates under different conditions will deepen considerably. The prospect of eventually visiting these worlds with robotic probes remains firmly in the realm of future generations rather than current plans, because the vast distances involved mean that even with optimistic assumptions about propulsion technology development, any mission to K2-18b launched today wouldn't arrive for thousands of years at conventional rocket speeds. Breakthrough propulsion concepts like fusion drives, antimatter engines, or laser-pushed light sails could potentially reduce travel times to centuries or decades, but developing such technologies requires fundamental advances that may or may not prove feasible. And the engineering challenges of building spacecraft that can survive interstellar journeys and operate autonomously for decades or centuries after launch dwarf anything humans have attempted. The question of whether we should send probes to potentially inhabited worlds if we develop the capability raises ethical issues about contamination and interference with alien ecosystems, because even microorganisms on Earth can survive in environments that seem inhospitable, and spacecraft sterilization procedures might not eliminate all terrestrial microbes, creating risk that we could inadvertently seed other worlds with Earth life that outcompetes or hybridizes with native organisms. The planetary protection protocols that govern solar system exploration would need updating to address interstellar missions, and the international community would need to develop consensus about what activities are appropriate when dealing with confirmed inhabited worlds versus sterile planets where introducing Earth life might not cause harm. The reverse contamination question of whether alien microorganisms brought back to Earth could pose biohazards probably worries more about science fiction than genuine risk for any mission to a world like K2-18b, because organisms adapted to completely different biochemical conditions likely couldn't function in Earth's environment. But the possibility cannot be entirely dismissed without actual knowledge of what alien biochemistry looks like. prudence suggests quarantine protocols for any sample return missions from potentially inhabited worlds, though the practical challenges of maintaining absolute containment through atmospheric re-entry, landing and laboratory analysis have never been tested with actual extraterrestrial samples beyond moon rocks and meteorites that arrived naturally. The search for life beyond Earth represents humanity's attempt to answer one of the oldest and most profound questions we've ever asked, and every new observation brings us incrementally closer to either finding the answer or understanding why the answer remains elusive. K2-18b might be the planet that finally provides definitive evidence, or it might be remembered as an important stepping stone toward that eventual discovery on some other world we haven't even identified yet. And regardless of how this particular case resolves, the search will continue because the question's importance transcends any individual result. The universe contains billions of potentially habitable worlds just in our galaxy alone, and the statistical likelihood that Earth is the only planet to ever harbour life seems vanishingly small given the vast numbers involved. Yet statistics don't guarantee anything, and we won't know for certain until we actually find life somewhere else. Each new detection of an exoplanet atmosphere, each refinement of biosignature search techniques, each improvement in telescope technology moves us closer to that moment of discovery, and the excitement lies not in knowing when it will happen, but in recognizing that it could happen any day as new data arrives from Webb or some future telescope and reveals unmistakable signatures of biological activity. The K2-18b findings remind us that we live in an extraordinary time when answering profound questions about our cosmic context has shifted from philosophical speculation to observational science, and previous generations could only wonder whether other worlds existed and whether any of them harboured life. But we can now detect those worlds, characterise their properties, and search for signs of life using instruments we've built with our own hands. The fact that we're having debates about whether specific molecules detected in a specific exoplanet's atmosphere represent signs of life demonstrates how far we've come and hints at how much farther we can go as technology improves and our observational capabilities expand. This is the frontier of human knowledge being pushed outward in real time, and the uncertainty and controversy surrounding K2-18b's biosignature detection reflects the genuine difficulty of doing science at the absolute cutting edge of what's possible, and the answers will come through persistence, careful work, and continued investment in the tools and people needed to pursue these questions. Each step forward opens new questions and new possibilities that previous generations couldn't have imagined, and the journey of discovery continues regardless of whether any individual result proves correct or turns out to be a false positive along the way. The next generation of space telescopes after Webb and Roman will likely include missions specifically optimized for characterizing terrestrial exoplanet atmospheres, and these instruments will combine large collecting areas for maximum sensitivity with advanced coronagraphs or starshades to suppress stellar glare and high-resolution spectrographs capable of dissecting atmospheric spectra in unprecedented detail. These future observatories might observe dozens or hundreds of potentially habitable planets during their lifetimes, building up the statistical sample needed to determine how common life really is. Ground-based telescopes also continue advancing, and the next generation of extremely large telescopes under construction includes the 30-metre telescope, the Giant Magellan Telescope, and the European Extremely Large Telescope, all scheduled to begin operations in the early 2030s. These facilities will work alongside space telescopes, providing complementary observations at wavelengths, where Earth's atmosphere is transparent, and offering the flexibility to respond quickly to new discoveries or sudden events. The theoretical and computational side of the field is advancing just as rapidly as observational capabilities, and researchers are developing increasingly sophisticated models of exoplanet atmospheres that account for complex chemistry, cloud formation, atmospheric circulation, and the intricate interplay between radiation and matter. These models help interpret observations by predicting what spectral signatures different atmospheric compositions should produce, and they also guide observers by identifying which molecules are most likely to serve as reliable biosignatures under various planetary conditions. Laboratory experiments complement theoretical work by measuring the physical and chemical properties of relevant molecules under conditions relevant to exoplanet atmospheres, and researchers create these conditions in vacuum chambers, high-pressure cells, and specialized spectroscopy setups that simulate the temperatures and pressures found on distant worlds. The spectroscopic databases that astronomers rely on to interpret telescope observations all derive ultimately from laboratory measurements, and improving the accuracy and completeness of these databases directly translates into better atmospheric characterizations. Machine learning and artificial intelligence are increasingly being deployed to help analyze exoplanet data, and neural networks can learn to recognize subtle patterns in spectroscopic data that traditional analysis methods might miss, while also helping to distinguish real signals from instrumental artifacts. AI systems are also being used to optimize observing strategies, determining which targets to observe and for how long to maximize the scientific return given limited telescope time. The human element remains crucial despite all the technological advances, and ultimately it takes careful scientists exercising sound judgment to interpret complex data and draw appropriate conclusions. The K2-18b controversy demonstrates the scientific process working as intended, with researchers proposing a provocative finding that others immediately scrutinize and test using independent methods. The debate will continue until either the evidence becomes compelling enough to convince skeptics or alternative explanations prove more convincing to the detection's proponents. Whether K2-18b truly harbours life, or whether this detection proves to be a false alarm, the planet has already secured its place in astronomical history as the first exoplanet where potential biosignatures were reported at statistically significant levels, and the intense scrutiny this claim has received will shape how future biosignature searches are conducted and reported. The lessons learned from this case will help the community develop better standards for evaluating evidence and communicating findings to both scientific peers and the public. The search for life beyond Earth represents humanity's attempt to answer one of the oldest and most profound questions we've ever asked, and every new observation brings us incrementally closer to either finding the answer or understanding why the answer remains elusive. K2-18b might be the planet that finally provides definitive evidence, or it might be remembered as an important stepping stone toward that eventual discovery on some other world we haven't even identified yet. The universe contains billions of potentially habitable worlds just in our galaxy alone, and the statistical likelihood that Earth is the only planet to ever harbour life seems vanishingly small given the vast numbers involved, yet statistics don't guarantee anything, and we won't know for certain until we actually find life somewhere else. Each new detection of an exoplanet atmosphere, each refinement of biosignature search techniques, each improvement in telescope technology moves us closer to that moment of discovery, and the excitement lies not in knowing when it will happen, but in recognizing that it could happen any day. The K2-18b findings remind us that we live in an extraordinary time when answering profound questions about our cosmic context has shifted from philosophical speculation to observational science. Previous generations could only wonder whether other worlds existed and whether any of them harbored life, but we can now detect those worlds, characterize their properties, and search for signs of life using instruments we've built with our own hands. The fact that we're having debates about whether specific molecules detected in a specific exoplanet's atmosphere represent signs of life demonstrates how far we've come and hints at how much farther we can go. This is the frontier of human knowledge being pushed outward in real time, and the uncertainty and controversy surrounding K2-18b's biosignature detection reflects the genuine difficulty of doing science at the absolute cutting edge of what's possible. The answers will come through persistence, careful work, and continued investment in the tools and people needed to pursue these questions, and each step forward opens new questions and new possibilities that previous generations couldn't have imagined. If you found this deep dive into the K2-18b controversy fascinating and want to stay updated on how this story develops, make sure to hit that subscribe button and turn on notifications so you don't miss future videos covering the latest discoveries in astronomy and the search for life beyond Earth. Drop a like if you appreciate the detailed breakdown of both the exciting possibilities and the legitimate concerns surrounding this detection, and let me know in the comments whether you think the biosignature is real or whether it's likely to be a false alarm. The answer matters less than the journey we're on to find out, and thanks for joining me on this exploration of one of the most important scientific questions humanity has ever pursued.